Hello fellow sapiens, and welcome to Sleepless Homo. This is slow storytelling for the restless hours. Whether you're preparing to sleep, or just letting your thoughts wander while working, cooking, or even standing in the shower. However you found this moment, you're invited to settle into it. If you appreciate this kind of calm, educational long-form content, consider liking the video and subscribing. It really does help, not only to support this channel, but to make sure other curious humans can find it too. I'd also love to hear from you. What do you use this kind of story for? Do you let it carry you off to sleep, or keep it with you while you work? Or perhaps just tell me where and when you're listening from, because this is not only a channel, it's a quiet gathering of minds, and if you happen to drift off during one of the chapters, don't worry. I've placed timestamps in the description, so the next day you can return and pick up the story exactly where you left it. The whole journey, from beginning to end, is worth experiencing. This channel is built on soft science, not wild speculation. We don't always have the answers, but we follow the evidence as humbly as we can, in search of clarity through deep time, and as always, stay curious, stay calm. Now, let's begin tonight's story, the first life on Earth, the complete story of our 4 billion-year-old beginning. Tonight we begin with a question that is older than the Earth itself. What is life? It seems simple when you glance at it. A blade of grass leaning toward the sun, a bird carrying food to its nest, your own lungs drawing in the oxygen that lets you sit here and listen. Life feels obvious, and yet when we try to pin it down in scientific terms, it slips away like water through our fingers. Why does it matter to define it before we look back in time? Because unless we know what we are actually searching for, the story of life's origin collapses into myth or metaphor. The oldest rocks on Earth hold traces of carbon, minerals, and long fossilized chemistry. But what counts as a living trace, and what counts as a lifeless stain, depends entirely on the definition we choose. When we say life began around 4 billion years ago, we are not pointing to a single fossilized creature, or a frozen moment when the universe whispered, "now." We are applying our definition. And here lies the first difficulty. Definitions are made by us, shaped by culture, philosophy, and the limits of our imagination. For much of human history, the definition was self-evident. Life begat life. A seed in the soil becomes a tree. A calf follows from its mother. The Greeks puzzled over how far this rule could stretch. Epicurus wondered if the cosmos itself had a kind of living breath. Aristotle claimed that life could spring spontaneously from certain kinds of matter, provided they carried a vital essence he called pneuma. For him, worms could grow from rotting flesh, and eels could emerge from damp riverbanks. His view persisted for nearly 2,000 years, not because it was true, but because no one could say precisely what life was or how it began. In the modern world, science has chipped away at this vagueness, but it has not solved it. Some biologists define life as that which grows, metabolizes, and reproduces. Others prefer to focus on information, saying life is anything that stores a genetic code and passes it on. NASA, famously, has defined life as a self-sustaining chemical system capable of Darwinian evolution. That phrasing is practical, designed for the search for extraterrestrial life, but it is also unsatisfying. Fire spreads, consumes fuel, and can even be said to reproduce itself under the right conditions. Crystals grow, propagate, and display intricate ordered structures. Computer viruses replicate and evolve. Are these alive? Most scientists say no, but why not? Because there is a subtlety hidden in the machinery of cells that crystals, flames, and viruses lack. To frame the search for our origin, we must strip life down to its simplest known essence. At its most basic, every living thing on Earth combines two features. The first is a self-replicating molecule that carries information forward. In modern biology, that role is played by DNA, the long double helix that stores instructions for building and maintaining an organism. The second is a metabolism, a set of chemical reactions that harvest energy from the environment and put it to work. These two features together create a feedback loop, instructions that build the machinery, and machinery that preserves and copies the instructions. Neither alone is quite enough. A molecule without metabolism is inert. A metabolism without instructions is chaos. Only the partnership can persist, adapt, and evolve, And yet, even this apparently clear definition stumbles on the edge cases. Viruses possess a genetic code and can evolve, but they lack their own metabolism and must hijack the chemistry of a host cell. Are they alive or not? Some say they are not alive at all, just infectious packets of information. Others argue they represent a twilight form, blurring the line between living and non-living, and perhaps even preserve clues to life's origin. On the other side, we have prions, simple misfolded proteins that can convert normal proteins into their twisted shape. They spread like an epidemic, yet contain no genetic code. Are they alive? Most biologists would deny it, but the denial reveals our uncertainty. It is tempting to think the problem is semantic, that we argue only about words. But in fact, it is deeply practical. If we do not know what life is, how can we recognize its beginnings on the early Earth? When we examine rocks from 3.5 billion years ago, how can we be sure whether a carbon trace represents an ancient microbe or a lifeless chemical stain? If we send probes to Mars or Europa, how will we distinguish a true alien organism from a chance chemical structure that only looks alive? Definitions do not just shape philosophy, they guide the hunt. Consider also the way definitions shape our perspective of ourselves. If life is defined as growth and reproduction, what does that mean for sterile individuals or for humans who live with artificial support systems? If life is defined by metabolism, are frozen embryos alive? If life is defined by Darwinian evolution, are lineages that reach a dead end considered less alive than those that persist? These questions push the boundaries of science into ethics, but they underscore the same truth. Our categories are imperfect, and yet they matter. In the end, perhaps life is less of a single trait than a bundle of traits that come together in one fragile package. A living system is not defined by any one property but by the combination, by the way the parts sustain one another. Energy capture, information storage, replication, adaptation. All of these are necessary. None alone is sufficient. That is why, when we search for the first life, we must look not for a single spark, but for the moment when chemistry began to organize itself into a loop that could persist. There is humility in admitting how much we do not know. No scientist today can point to the exact moment when non-living matter tipped into life. We cannot reconstruct the first living cell in a laboratory, no matter how sophisticated our techniques. Every definition we give is provisional, a tool to help us reason rather than a final truth. But without the tool, the story of life's origin becomes ungraspable. Before we can peer into the ancient oceans of 4 billion years ago, we must first agree on what we're even looking for. So here is the haunting question to carry forward. If life is a set of processes rather than a fixed essence, then is it a thing that exists in the world, or is it a category we invent to make sense of patterns in chemistry? When we say life began, are we describing an event in nature? Or are we drawing a line across a continuum declaring this side is living, that side is not? Perhaps there was never a single moment, only a long gradient where molecules grew more complex until at some point they crossed a threshold we now recognize as familiar. If that is true, then the question of life's beginning may never yield a simple answer, because it was never a simple event. What we can do is proceed cautiously, acknowledging our ignorance, setting our definition as clearly as possible, and then tracing the evidence step by careful step. We will not always have the answers, but we can at least define the mystery. That is where the story begins, and so the stage is set. We know that life must involve both information and metabolism, yet we know the boundary is blurred. We know that life did not exist on the newborn Earth, and yet it exists today in abundance. The question is not whether life emerged, but how. That search carries us back into the ancient world of chemistry and oceans, long before the first fossils, long before the first microbes, long before even the continents we stand on. But before we follow it there, pause and consider the thought. When we say life, what do we mean? The answer is uncertain, the search is humbling, and the story is about to unfold. How can life begin on a world that seems designed to kill it? To imagine the earliest Earth is to imagine a place so violent, so unstable, and so profoundly hostile that it strains belief that anything soft and fragile could have ever taken root there. We call this time the Hadean, named after Hades, the Greek underworld, not because it contained fire and demons, but because it was a place that seemed, by all appearances, entirely unfit for life. From about 4.5 billion years ago, when the Earth first coalesced from cosmic debris, until around 4 billion years ago, when the earliest crust began to stabilize, our planet was a furnace, a target, and a battlefield. It was a planet not meant for life, yet it is the only place we know where life began. The Earth's birth itself was violent. Our planet grew out of a disk of dust and gas that circled the young sun. Tiny grains clumped together into pebbles, pebbles into boulders, and boulders into planetesimals, each collision releasing more energy. By the time the Earth reached its full size, the entire globe had been melted into what scientists call a magma ocean. Imagine the surface not as rock and soil, but as a boiling incandescent sea of molten minerals, constantly convecting and overturning, glowing red like the coals of a furnace. This was not a surface that any delicate chemistry could survive upon. Worse still, the young Earth was bombarded by leftover planetary fragments. For hundreds of millions of years, asteroids and comets crashed into the surface with unimaginable force. Some were large enough to vaporize oceans. Others may have struck with enough power to briefly reliquefy large parts of the crust. And in one particularly catastrophic event, sometime around 4.5 billion years ago, a Mars-sized body collided with the Earth. The violence of this impact ripped away part of the Earth's mantle and ejected it into space, where it coalesced into the Moon. Without that collision, we would have no tides, no lunar beacon, and perhaps no stability in our planet's axial tilt. Yet at the time, it must have erased any hope of calm. During the Hadean, water came and went in cycles of destruction. We think that much of Earth's initial water may have boiled away during its molten youth, stripped by solar winds or blasted into space by impacts. But water is a stubborn molecule. It may have returned through later impacts by icy comets or hydrated asteroids, or it may have been drawn up from the mantle, trapped deep within minerals and gradually released by volcanic outgassing. However it came, the early oceans did not remain stable. Each large impact could boil them off again, leaving a scorched, vapour-shrouded planet until they condensed once more. This cycle of loss and return may have repeated many times before the oceans we know today became permanent features. The atmosphere was no gentler. Instead of oxygen and nitrogen in the balance we breathe now, the Hadean air was thick with carbon dioxide, nitrogen, water vapour, methane, ammonia, sulphur compounds, and whatever gases escaped from endless volcanic eruptions. Lightning ripped through clouds of steam and ash. The sun itself, though fainter than today, bathed the surface with harsh ultraviolet light, unfiltered by ozone because no oxygen existed yet to produce it. From space, the planet might have looked beautiful, a glowing ball veiled in swirling vapour. Up close, it was catastrophic. And yet, slowly, a kind of order began to emerge out of this chaos. Even in the midst of bombardment, the Earth's crust began to stabilize. Minerals crystallized out of the magma ocean, forming the first proto-continents. Zircon crystals, some of which have been dated to over 4 billion years old, tell us that solid crust existed earlier than we once thought, and that liquid water pooled on the surface at least intermittently, even during this infernal era. These zircons are tiny, barely visible to the naked eye, but they are among our only direct windows into a world where no rocks remain. Their isotopic fingerprints suggest not only that continents were forming, but that rainfall and weathering had already begun to reshape the land. This detail matters. If the Hadean Earth had remained forever molten, life could never have taken hold. But the evidence suggests there were pauses between the bombardments, moments of relative calm where crust solidified, oceans pooled, and environments stable enough for chemistry to persist took shape. Perhaps they were brief, perhaps they were fragile, but they were there. The Earth was not a uniform hellscape. It was a patchwork of fire and water, destruction and reprieve. Consider the role of the Moon, born of that ancient collision. Its gravitational pull stabilized the Earth's rotation, preventing chaotic shifts in tilt that might otherwise have thrown climate into extreme swings. The tides it raised would have stirred the oceans, mixing minerals and water. Without the Moon, the Hadean might have remained permanently unstable. Instead, the Earth began, against all odds, to settle. Volcanoes pumped out gases that thicken the atmosphere. The greenhouse effect they created may have kept surface water from freezing even under a fainter young sun. Impacts that vaporized oceans may also have delivered new ingredients, replenishing what was lost. And each time the Earth was struck, each time its surface was scoured, it began again. In the balance between destruction and renewal, opportunities for stability gradually increased. We must be careful not to romanticize this world. It was not nurturing in any way we understand. It did not welcome life. If anything, it did everything possible to erase it. But the fact that our planet cooled at all, that water condensed, that crust solidified, shows us that even on a planet designed to kill, windows of habitability opened. These were the fragile cracks in which the story of life could one day take root. As scientists, we cannot reconstruct every detail. We do not know exactly when the magma ocean fully solidified. We do not know how many times the oceans were boiled away, or how many continents briefly rose and sank again. What we do know comes from scattered isotopes in tiny minerals, from models of planetary formation, and from comparisons with other bodies in our solar system. The Moon preserves a record of bombardment that the Earth's tectonic churn erased. Mars shows us what a smaller, less active planet looks like after billions of years of exposure. Together, these comparisons suggest that while the Hadean was violent, it was also transitional. Here is the haunting question. If the Earth of 4.5 to 4 billion years ago was truly unfit for life, then does that mean life had to wait until the violence subsided? Or did it somehow begin even in the midst of this chaos, surviving through bombardment after bombardment in protected niches, perhaps in the depths of the ocean or beneath the crust? Was life delayed, or was it already struggling forward while the planet still seemed bent on its destruction? We do not yet know. The traces of that time are nearly all erased, recycled by plate tectonics and buried by eons of geology. But we do know this. Our story begins not in a calm, fertile world, but on a planet that looked like it should have been sterile. And yet, it was here, in this improbable environment, that the possibility of life was born. So we are left with an unsettling thought. If life can emerge on a planet that seemed designed to extinguish it, then perhaps life is not as fragile as we imagine. Perhaps the seeds of persistence are written into the universe itself. Or perhaps we are simply lucky, the beneficiaries of rare reprieves in a world of fire. Either way, the story that follows begins with this paradox. Earth was a planet not meant for life, and yet life found its way. To imagine the Hadean Earth in greater detail is to accept that much of what we know comes not from surviving rocks, but from indirect traces and careful comparisons. The crust from this time has been almost entirely recycled. Yet in Western Australia, in a region called the Jack Hills, scientists have found tiny zircon crystals, only fractions of a millimetre across, that hold within them chemical whispers of this vanished world. Some of these zircons date back to more than 4 billion years ago. Their chemistry shows that they formed in the presence of liquid water, and at relatively low temperatures, suggesting that even during the Hadean there were moments when oceans lapped against solid land, when rain fell, when water carved and weathered rock. That alone is remarkable, for it means that the Earth was not in a permanent state of fire, but had windows of calm long before life is thought to have appeared. The isotopes of hafnium preserved inside those zircons also hint that continental crust existed by this time. Continental crust is different from the dark, dense rock of ocean basins. It is lighter, richer in silica, and more buoyant, floating higher on the mantle. The fact that this crust was already forming implies that the tectonic engines of Earth were turning early, recycling rock, creating stability, and shaping a surface more diverse than a single global ocean. Again, these findings challenge older pictures of the Hadean as a wholly molten inferno. The truth is more nuanced. It was hellish, yes, but it also contained the seeds of habitability. One of the great debates in planetary science is the role of the so-called late heavy bombardment, a theorized spike in impacts around 3.9 billion years ago. The evidence for this spike comes primarily from lunar samples, collected during the Apollo missions. Many of the Moon's great basins, like Imbrium and Oriental, seem to date to this narrow window of time. If the Earth was struck just as heavily, its oceans might have been repeatedly sterilized, boiling away and then condensing again after each massive impact. Some scientists argue this bombardment reset the clock for life, meaning nothing permanent could have taken root until it subsided. Others think the evidence from the Moon may be biased, and that impacts were more spread out. If so, then the Earth's surface may have had longer intervals of relative calm where chemistry could proceed. Either way, what we know is that bombardment did not prevent life altogether, because within a few 100 million years of this period, the first signatures of living processes appear in the geological record. Comparisons with our planetary neighbours sharpen the picture. Venus, about the same size as Earth, may have once had water but seems to have lost it early. Its thick carbon dioxide atmosphere and crushing heat suggest a runaway greenhouse effect. Mars, smaller and cooler, preserves ancient valleys that look as though rivers once flowed across its surface. But Mars lost much of its atmosphere to space, becoming too cold and too dry to sustain life as we know it. Earth is the outlier, the planet that managed to hold on to its water, to stabilise its atmosphere, and to maintain conditions that could eventually nurture life. Why Earth succeeded where Venus and Mars failed remains one of the deepest questions in planetary science. Perhaps it was our magnetic field, generated by a molten iron core that shielded the atmosphere from solar winds. Perhaps it was plate tectonics, constantly recycling carbon and regulating climate. Perhaps it was the lucky balance of impacts that delivered ingredients without destroying all progress. Whatever the reason, Earth's path was not inevitable. It was contingent, fragile, and precarious. It is worth pausing on what this means. The Hadean Earth was not a uniform story of fire or of calm. It was a shifting mosaic, a world where oceans could exist in one epoch and vanish in another, where land could rise and then sink, where impacts could erase whole landscapes. For hundreds of millions of years, the planet was a canvas that kept being repainted. Yet through this cycle of destruction and renewal, conditions favourable to life kept returning. Stability was temporary, but it was not absent. For scientists, the challenge is to imagine how chemistry might proceed in such a world. Could fragile molecules survive the heat of impacts? Could they hide in deep rock pores, in volcanic basins, or beneath the sea floor where the violence of the surface could not reach? Or did life have to wait, biding its time until the bombardment waned and the crust thickened into something resembling permanence? We cannot yet answer this. What we can say is that by 4 billion years ago, the Earth was no longer just a molten sphere. It had oceans, it had some crust, it had weather, rain, and rivers, it had an atmosphere thick with gases. It was no longer just a planet of fire, it was beginning to be a world. And yet, for all of this, it still seemed designed to erase what might arise. Ultraviolet light bombarded the surface, breaking apart molecules. Impacts could reset the stage in a single blow. Volcanoes could smother landscapes. Oceans themselves may have been hot, acidic, and unstable. To ask how life could begin here is to ask whether persistence is stronger than destruction, whether the universe has a bias toward survival even in its most unwelcoming corners. The haunting thought remains that if Earth could move from such hellish beginnings into a place where life is possible, then perhaps other planets too may hide their own improbable stories. Or perhaps it was only here, with just the right balance of catastrophe and calm, that the long chain leading to us could begin. In either case, the Hadean Earth was not meant for life, but it became, against all odds, the cradle in which life's possibility first stirred. If life is chemistry, then the obvious question is where the chemistry itself comes from. We live on a planet that is rich in carbon, nitrogen, oxygen, and hydrogen, along with traces of sulfur, phosphorus, and dozens of other elements. These are not Earth's inventions. They are the legacy of stars, the very atoms in our bodies, in the rocks beneath our feet, and in the water we drink were forged in nuclear furnaces long before Earth itself existed. To understand how the first life could begin, we must first accept that the ingredients were not born here. They were delivered, scattered, and reshaped across cosmic distances, written into matter long before the Earth's oceans cooled. The story begins in ancient stars generations before our Sun. When massive stars live and die, they create the heavier elements through nuclear fusion and then scatter them across the galaxy in supernova explosions. Carbon, nitrogen, oxygen, and iron are all products of this stellar cycle. Even elements like phosphorus, so vital to DNA and energy molecules, trace their origins to supernovae. In this sense, the chemistry that would one day power life was seeded billions of years before Earth was born. Our solar system is the child of that debris, formed from a cloud of gas and dust enriched by countless stellar deaths. This is why astronomers sometimes say that life is star stuff. It is not a metaphor, but a literal statement of origin. As the solar system coalesced around 4.5 billion years ago, the Sun ignited at its centre, and a protoplanetary disk of gas and dust spun around it. In this disk, the raw materials for Earth were already infused with molecules of surprising complexity. Observations of young star systems elsewhere in the galaxy, using telescopes like ALMA, have revealed chemical signatures of amino acids, sugars, and other organic molecules forming in such disks. Laboratory simulations and spectroscopic studies of interstellar clouds support this as well. Ice-coated dust grains drifting between the stars can act as tiny laboratories. Ultraviolet light and cosmic rays strike these icy grains, breaking bonds and allowing atoms to recombine into new forms. Amino acids, the building blocks of proteins, can emerge in this cold chemistry of space. Simple sugars like ribose have been detected in meteorites that fell to Earth. Their origins trace back to similar processes. Meteorites themselves provide some of the strongest evidence. In the mid-20th century, scientists studying the Murchison meteorite, which landed in Australia in 1969, found that it contained over 70 different amino acids, many not used by life on Earth. More recently, careful analysis has identified nucleobases, the very same molecules that form the rungs of DNA and RNA. Ribose, a sugar central to nucleic acids, has also been found. These discoveries tell us that the universe is not barren of life's ingredients. They form naturally, given the right conditions, long before any planet provides a surface for life to emerge. Earth did not invent these molecules, it inherited them. During the violent formation of our planet, Earth was constantly bombarded by asteroids, comets, and cosmic dust. Each impact was a potential delivery of new organics. Some scientists have estimated that hundreds of millions of tons of extraterrestrial material may have rained down on Earth during its early history. Comets, rich in ices and carbon compounds, could have seeded the surface with complex molecules. Even tiny interplanetary dust particles drifting down through the atmosphere could carry organics, surviving entry and sprinkling them into oceans and soils. Though the planet was hostile, chemistry was not waiting for Earth to calm. It was arriving constantly, in every fiery streak across the early sky. It is important to stress that this does not mean life itself came from space. The theory of panspermia, which suggests life may have been carried fully formed on comets or meteorites, remains speculative and unproven. What we do know with far greater confidence is that the building blocks of life were present, delivered and abundant. Carbon chemistry is remarkably versatile, and under the right conditions it tends to grow more complex. That is what we see in meteorites, in interstellar clouds, and in laboratory simulations. So the early Earth, even as it boiled and cooled, was already a stage filled with potential ingredients. One of the haunting questions is how much of this extraterrestrial chemistry survived the violence of the Hadean environment. If impacts were large enough to vaporize oceans, would not the delivered molecules be destroyed as well? Here, again, scale matters. Large impacts may indeed have sterilized wide regions, but smaller impacts, more frequent and less catastrophic, could have continuously replenished what was lost. Furthermore, much of the material may have been shielded inside rocks, delivered intact even through fiery entry. The cosmic rain was relentless, and even if most molecules were destroyed, enough could accumulate in sheltered environments, in pools, in soils, or deep under rock. Our understanding of this process comes not only from geology, but also from astronomy. Observations of comets in our solar system show that they contain organic compounds in abundance. When the Rosetta spacecraft studied Comet 67P, 𝐓𝐈𝐌𝐄𝐒𝐒, it detected glycine, one of the simplest amino acids, along with other organics. These are not rare accidents, they appear to be a common feature of icy bodies. If comets and asteroids delivered such chemistry to Earth, they could have enriched the planet enormously. The humble tone of this story is necessary. We must admit that we do not know the full details. The early record has been wiped away by time, and we can only piece it together from fragments. But the evidence that organics existed before life is overwhelming. We find them in meteorites, in comets, in interstellar dust. The ingredients are older than Earth. That realization is profound because it suggests that life is not a rare accident of this one planet, but a natural consequence of chemistry in the universe. If amino acids and sugars can form in the cold darkness of space, then perhaps the leap from non-life to life is not as improbable as it once seemed. To bring this back to Earth's molten infancy, picture oceans still young, heated from below by a restless mantle, and from above by an active sky. Into these waters fell fragments of rock and ice from beyond, each carrying chemistry born in stars. The seas may have been hostile, but they were not empty. They were becoming repositories of the galaxy's handiwork. Every drop of water could have contained traces of molecules that had travelled light years, only to dissolve into the world that would one day harbour living cells. What we can say, with humility, is that by 4 billion years ago the Earth was not just a geophysical body, it was a chemical crucible, charged with ingredients both terrestrial and cosmic. We cannot say which molecules mattered most, or how many steps were necessary before they linked into something that could copy itself, but we can say the starting materials were present in staggering abundance. The Earth was not a blank canvas, it was a collage of chemistry painted by stars, and here lies the haunting question. If the universe delivers life's ingredients so freely, why has life itself not been detected elsewhere? Are we missing it, looking in the wrong ways, or is there some hidden barrier between chemistry and biology that only Earth crossed? We do not know. What we do know is that our world inherited the seeds, and on this molten ocean planet, those seeds began their long and uncertain transformation into what we now call life. Why did human beings believe for nearly 2,000 years that life could simply appear from rotting meat, damp soil, or stagnant water? The idea of spontaneous generation may sound strange to us now, but for most of recorded history, it was not only common sense, but the dominant explanation for how worms, flies, and even mice appeared in the world. To understand why the origin of life is a modern scientific problem rather than an ancient one, we must step back and look at how earlier generations framed the question. Their answers were not silly guesses, but reflections of the limits of what they could observe. They lived in a world without microscopes, without germ theory, and without the modern concept of molecules. For them, seeing was believing, and what they saw was that life seemed to erupt from decay. In ancient Greece, Aristotle gave the most influential articulation of this idea. Writing in the 4th century before the Common Era, he proposed that many living things were generated spontaneously from non-living matter. Worms from mud, flies from rotting flesh, and even eels from the guts of wet soil. To him, this was not myth, but observation, a way of explaining the sudden appearance of creatures where none had been seen before. He believed in a vital heat, an animating force that could shape matter into life under the right conditions. This theory fit neatly with his broader philosophy of nature, which saw forms and purposes driving all things. In Aristotle's framework, life did not require a special creation each time. It could arise naturally whenever the right mixture of warmth, moisture, and matter allowed it. This view became deeply embedded in Western thought. For centuries it was repeated, elaborated, and extended. The Roman writer Pliny the Elder echoed the idea, describing animals born from putrefaction. In medieval Europe, encyclopedias and bestiaries repeated stories of spontaneous birth. By the 17th century, some natural philosophers even proposed recipes. Jan Baptista van Helmont, a Flemish chemist and physician, famously suggested that mice could be generated by placing a dirty shirt in a container with wheat. Within 3 weeks, he wrote, adult mice would appear, male and female, ready to reproduce. It is easy to laugh at this today, but in a time before controlled experiments and microbiology, such a recipe seemed plausible. After all, houses did seem to fill with mice where grain was stored. Where else could they have come from? The persistence of spontaneous generation tells us something important about human knowledge. For most of history, people did not ask where life originally came from. They assumed life was a permanent feature of the world, cycling endlessly through birth, death, and rebirth. The question of the very first life was not even framed. Instead, they asked how life continued to arise in the everyday world. Spontaneous generation was not about the deep past, but about the present. It was an explanation for the constant renewal of the living around us. The challenge to this idea only came slowly. In the 17th century, the invention of the microscope by pioneers like Antony van Leeuwenhoek revealed a hidden world of tiny creatures teeming in droplets of water and in the scum scraped from teeth. These animalcules, as he called them, seemed to appear just as suddenly as worms in soil. To many, this confirmed rather than contradicted spontaneous generation. If such minute beings could emerge without parents, then perhaps all life, great and small, could. Yet others began to doubt. The Italian physician Francesco Redi conducted one of the earliest controlled experiments in the 1600s. He placed meat in jars, some open, some sealed, and some covered with gauze. Flies appeared only when they could reach the meat, not when the jars were sealed. From this he argued that maggots were the offspring of flies, not the product of decaying flesh itself. His work did not settle the matter, but it planted the seed of doubt. Through the 18th century the debate grew. Some experiments suggested that boiling broth could prevent the appearance of microorganisms, hinting that they were not spontaneously generated but introduced from outside. Others argued that boiling destroyed the vital force needed for life to arise, so the absence of organisms in boiled broth proved nothing. The French naturalist Buffon, one of the era's great thinkers, leaned toward spontaneous generation, seeing it as a natural extension of his materialist worldview. Yet skeptics continued to refine their tests, trying to separate cause from coincidence. It was not until the 19th century that the question was addressed decisively. The French chemist Louis Pasteur conducted a series of meticulous experiments in the 1860s that finally discredited spontaneous generation as a scientific theory. Using swan-necked flasks filled with nutrient broth, he showed that sterilized liquids remained free of microbial life so long as airborne particles were excluded. When the necks of the flasks were broken, microorganisms soon appeared. Pasteur's conclusion was simple. Life does not arise spontaneously under present conditions. It comes from life. Omne vivum ex vivo, every living thing from a living thing. The rejection of spontaneous generation was not just a triumph of experimental technique. It marked a profound shift in how we frame the question of life's origins. Once spontaneous generation was ruled out, the origin of the very first life became a mystery again. If life does not just appear from non-living matter today, how did it ever appear at all? Pasteur himself, while discrediting spontaneous generation in the laboratory, did not claim to solve the ultimate problem. He hinted that life may have been created once, long ago, or introduced from elsewhere, but the question remained open, and in a sense it has remained open ever since. What is striking is how long humanity lived with an explanation that now seems so obviously wrong. But that judgment is easy with hindsight. Without microscopes, without knowledge of microbes, without an understanding of reproduction at the cellular level, spontaneous generation was a rational inference. It reflected human attempts to make sense of everyday phenomena. Insects did emerge from dung. Frogs did seem to appear in mud after rain. To see these events as transformations of matter into life was natural. The true explanation required tools and concepts that only modern science could provide. We should also acknowledge that the death of spontaneous generation did not come without resistance. Some clung to the old ideas even after Pasteur's experiments. Others suggested modified theories such as abiogenesis in limited circumstances. The word itself has changed meanings over time. In the 19th century, abiogenesis was often used as a synonym for spontaneous generation, whereas today it refers to the origin of life from non-living chemistry in the deep past. This shift in language reflects the evolution of thought. The debate moved from whether life arises anew in everyday settings to how it first arose billions of years ago. By tracing this history, we see why the modern problem of life's origin is so different from the ancient one. For Aristotle and Van Helmont, the appearance of creatures from decay was explanation enough. For us, the real puzzle is the transition from non-life to life in a world where we now know it does not happen under ordinary conditions. The difficulty is sharper precisely because spontaneous generation has been excluded. We no longer believe that flies or microbes pop out of nothing. So how did the very first cell come to be? The resolution of the spontaneous generation debate sharpened the mystery rather than solved it. It pushed the question further back in time, beyond recorded history, beyond fossils, to an era when Earth itself was young. Pasteur's experiments closed one door and opened another. The haunting question is the one that remains. If life does not arise spontaneously in front of our eyes, what chain of chemistry allowed it to arise once, 4 billion years ago, when the Earth was still cooling from its birth? Was there really a primordial soup, or is that just a piece of lazy shorthand we keep repeating because it is catchy? When people talk about the origins of life, they often imagine a dark, steaming cauldron of chemicals sloshing around on an alien Earth, waiting for lightning to strike and create something alive. It is an image so simple and evocative that it has clung to textbooks, documentaries, and popular imagination for nearly a century. Yet the truth, as far as we can reconstruct it, is less like a single pot of soup and more like a planet-sized experiment happening in countless environments at once. Before we talk about the first molecules that copied themselves, we should pause on this question. What was actually in Earth's oceans between 4.5 and 3.8 billion years ago? Because whatever the recipe was, it shaped the possibilities of everything that came later. To start with, the phrase primordial soup itself is older than most people realise. It traces back to the work of Alexander Oparin in the 1920s and John Haldane in the 1930s. They imagined that Earth's early oceans might have been rich in organic molecules formed under a reducing atmosphere. In this view, the seas were like a broth, filled with the ingredients of life. It was a neat metaphor, and it captured imaginations. But metaphors can sometimes mislead. Was the ocean really so rich in organics? And if it was, how long could those molecules last in such a vast and restless system? The question begins with the atmosphere. Today, Earth's air is mostly nitrogen and oxygen, but in the Hadean and early Archean, the balance was very different. Oxygen, as far as we know, was almost entirely absent. Instead, gases spewed from volcanoes and impact sites. Carbon dioxide, water vapour, methane, hydrogen, nitrogen, perhaps even ammonia and hydrogen sulfide. The precise mixture remains uncertain, and different models give different answers. Some researchers argue for a strongly reducing atmosphere, full of hydrogen-rich compounds. Others suggest a more neutral one, dominated by carbon dioxide and nitrogen, which would make it harder to produce complex organics. The truth may have shifted over time depending on volcanic activity, the bombardment of the surface by meteorites, and the gradual cooling of the planet. Into this unstable air fell torrential rains. As the crust cooled enough to hold liquid water, those rains filled the basins of the early Earth, creating vast oceans. These oceans were not the blue expanses we picture today. They were likely greenish or brown, tinted by dissolved minerals, acidic in some regions, alkaline in others, and constantly stirred by tides, currents, and impacts. In these seas, gases from the atmosphere dissolved and reacted. Lightning strikes, ultraviolet radiation from a sun not yet filtered by an ozone layer, and geothermal energy from below provided constant sparks. It was a world of chemistry in motion. In the 1950s, Stanley Miller and Harold Urey attempted to recreate such conditions in a laboratory. They sealed a mixture of gases thought to represent the early atmosphere, methane, ammonia, hydrogen, and water vapour, into a closed system and passed electrical sparks through it to mimic lightning. After a week, the flask contained a brownish residue rich in amino acids, the building blocks of proteins. It was a stunning result, one that seemed to confirm Oparin and Haldane's vision. Life's ingredients, it seemed, could form spontaneously in a soup of the right gases and water. The Miller-Urey experiment quickly became iconic, repeated in classrooms and television programs as the demonstration that the origin of life was not magic but chemistry. Yet even this celebrated experiment had limits. Later work suggested that Earth's early atmosphere may not have contained as much methane and ammonia as Miller assumed. If instead it was dominated by carbon dioxide and nitrogen, the yields of organic molecules would have been far lower. Replications of the experiment under those conditions produced fewer amino acids, sometimes only trace amounts. critics argued that the Miller-Urey setup was too idealized, too generous, compared with the harsher and less cooperative reality of the young Earth. In other words, the experiment may have demonstrated a possibility, but not necessarily the probability. Still, variations on the theme continued. Scientists found that adding volcanic gases like hydrogen sulfide or simulating impact shock waves could also generate organics. Ultraviolet light, once thought only destructive, turned out to drive some key reactions under the right circumstances. Even meteorites, particularly carbon-rich chondrites, were shown to carry amino acids and other complex molecules. This meant that the ocean's inventory could have been supplemented not only by Earth's atmosphere but by delivery from space. The soup was not a single pot but a network of sources: air, rock, water, and the sky above. The metaphor of soup, however, still has problems. A soup suggests a uniform broth, evenly mixed and stable, waiting for something to happen. The reality was probably nothing like that. Molecules in the open ocean would have been quickly diluted, broken apart by radiation, or destroyed by hydrolysis. Concentrating them enough for reactions to take place was a challenge. This is one of the main critiques of the soup idea. The ocean is vast and molecules in it are scattered. How could such a diluted system ever get chemistry moving toward life? One answer is that the ocean was not the only environment. Shallow ponds, tidal flats, drying lagoons, and volcanic pools could have provided the kind of concentration and cycling needed. Molecules washed in by rain or impact debris might have been trapped in films, clays, or mineral pores. Evaporation could increase concentrations, while repeated wet-dry cycles might drive polymerization reactions. In this view, the soup is not the whole ocean, but many smaller pots scattered across the planet. Each was an experiment in chemistry, most failing, some perhaps producing something stable enough to last. Another complication is that the soup metaphor tends to imagine ingredients floating freely, waiting to assemble. But in practice, molecules interact with minerals, with surfaces, with metals dissolved in water. Iron and nickel sulfides, for example, can catalyze reactions. Clays can hold nucleotides in their layers and help them join into longer chains. Even ultraviolet light, destructive at high doses, can act as a selective pressure, breaking unstable compounds while sparing more resilient ones. So the chemistry of the early ocean was not just passive mixing but active filtering. The soup was cooked, stirred, and strained by the planet itself. What then should we say? Was there really a primordial soup? The safest answer is that there were many different soups, none exactly like the cartoon version, all contributing in small ways to the molecular richness of the early Earth. The phrase may be shorthand, but it points toward a deeper truth. The ocean was never empty water. From the beginning, it was a stage for chemical experiments on a scale no laboratory can match. Whether it was rich enough, concentrated enough, or structured enough to cross the line into life remains uncertain. The legacy of the soup idea is not just scientific but cultural. For decades, it has been used as a teaching image, a way of making the abstract problem of abiogenesis tangible. It has shaped how generations think about life's beginning. Yet as research progresses, the metaphor may be holding us back as much as it helps. Modern work emphasizes cycles, gradients, and surfaces rather than a single uniform broth. The origin of life may not have been a soup at all, but a landscape of countless microenvironments, each cooking up its own chemistry. In this sense, the primordial soup is both a myth and a memory. A myth, because the oceans of 4 billion years ago were unlikely to resemble the simple recipe often described. A memory, because it captures the excitement of realizing that life could, in principle, emerge from ordinary chemistry. We should be cautious about taking the image literally, but we should also recognize its power as a stepping stone. Sometimes metaphors outlive their accuracy, but they continue to remind us of the questions that matter. So was there really a soup? Perhaps not in the way the textbooks once showed. But there were oceans full of molecules supplied by the sky, the rocks, and the cosmos beyond. Those molecules did not yet replicate or evolve, but they formed the backdrop against which the first steps became possible. And if the soup is a myth, it is a useful one, because it reminds us that even on a planet that seemed hostile, the sea was never truly empty. The haunting question is the one that lingers. If Earth's oceans 4 billion years ago held the molecules of life, why did only one path succeed? Were there countless false starts? chemical cul-de-sacs that vanished without trace, while one fragile chain endured. And if that is true, then how many other worlds may hold their own soups, or something like them, waiting silently for lightning, time, and chance? Which came first, the instructions or the machine? It is one of those questions that seem simple enough to ask but impossible to answer, without tying yourself into knots. At the heart of modern biology lies a paradox so deep that it almost feels like a riddle told by the universe itself. On one side, you have DNA, the molecule that holds the instructions for building and sustaining life. On the other, you have proteins, the molecules that do nearly all the work inside cells, from catalyzing reactions to stitching together new copies of DNA. Each is utterly dependent on the other, yet neither could have reasonably come first. If DNA needs proteins to replicate, and proteins need DNA to be built, then how could life have ever gotten started? This is not just a philosophical puzzle, though it has that flavour. It is a scientific problem of the most stubborn kind, one that has occupied generations of researchers. To understand the paradox, we must first appreciate the division of labour in the cell. DNA is like a library of instructions written in a 4-letter alphabet of nucleotides. Proteins are the workers, built from 20 amino acids, each folded into a precise shape to perform its function. The process of turning DNA into proteins requires a complex choreography. DNA must first be copied into RNA. That RNA must then be read by molecular machines called ribosomes, which themselves are partly made of proteins, to link together amino acids in the order dictated by the sequence. Enzymes, which are specialized proteins, are required at every step to unwind DNA, to synthesize RNA, to attach amino acids to transfer molecules, and to join those amino acids into chains. Without those proteins, DNA is a silent string of letters. Without DNA, proteins have no script to follow. The paradox is obvious when stated plainly. If the first life began with DNA, how was the first protein ever made? If it began with proteins, what instructed them how to form in the correct order? Neither molecule makes sense in isolation. It is like asking whether the recipe book or the cook came first. The cook needs a recipe, but the recipe is meaningless without someone to cook it. This circularity sits like a locked door in the middle of biology, and it is one of the reasons why the question of life's origin remains so difficult. Some have tried to sidestep the paradox by imagining that DNA might have formed spontaneously and been able, in some primitive way, to copy itself without proteins. But experiments show that DNA is too stable and too inert to carry out complex reactions without help. Others have tried the opposite idea, that proteins may have formed spontaneously and begun catalyzing reactions, but proteins are notoriously unfaithful. Without an instruction set, they assemble in random sequences, and only a rare few of those would fold into anything useful. The odds of stumbling across just the right sequence by chance are astronomically low, so both DNA first and protein first scenarios run into a wall. This is why scientists speak of a chicken and egg problem. The very features that make DNA and proteins so powerful today, their specificity, their reliability, their interdependence, make them terrible candidates for being the first molecules of life. It is like trying to start a play in the middle of Act 2, with the actors waiting for a script and the script waiting for the actors to bring it to life. Something simpler must have come before, something that could act both as instruction and as machine, collapsing the division we see today. The paradox of DNA and proteins also highlights just how elaborate even the simplest cells are. We often imagine bacteria as primitive, but the machinery inside them is staggeringly complex, involving hundreds of proteins working in concert with DNA and RNA. The very fact that this complexity is universal, shared by all known life, tells us it must trace back to the very beginning. Whatever the solution to the paradox was, it had to be in place before the last universal common ancestor existed more than 3.5 billion years ago. That ancestor already had DNA, already had proteins, already had the intricate translation machinery to move between them. So the paradox is not just a thought experiment. It is a window into a real transition that must have happened on the early Earth, and yet has left almost no trace for us to study. We might ask, could the paradox simply be an illusion of hindsight? Maybe the sharp distinction between DNA and proteins is a product of billions of years of evolution, and in the beginning the lines were blurrier. Perhaps molecules existed that could both carry information and perform some simple chemistry, blurring the cook and the recipe into a single form. The very idea forces us to think outside the categories we are comfortable with, because the neat separation of labour we see in cells today may not reflect the messy transitional steps of the past. Even so, the paradox remains useful because it acts like a signpost. It tells us that our explanations cannot simply start with DNA or proteins. They must look for something earlier, something capable of solving the dual problem of information and catalysis. The search has led to whole fields of research in molecular biology, biochemistry, and even astronomy, each trying to imagine what that simpler system might have been. But before we rush to those ideas, it is worth sitting with the paradox itself, because it reminds us of the limits of our knowledge. It reminds us that life as we know it depends on a partnership so tightly interwoven that pulling on one thread collapses the whole fabric. From a broader perspective, the paradox also forces humility. It is tempting to imagine that given enough time and chance, life was inevitable. But the paradox of DNA and proteins shows us just how improbable it seems when viewed through modern biology. If you set the conditions of early Earth and simply wait, is it really likely that such an interdependent system would arise? Or does the fact that it did happen suggest that we are missing some simpler, more natural path that made the improbable much more probable? This question hangs heavy over every discussion of abiogenesis. The paradox also resonates beyond science, touching philosophy and even humour. In casual conversation, people sometimes joke about the chicken and egg problem without realising that biology hides its own version, far deeper and less easily resolved. The difference is that with chickens and eggs, we know both existed and evolved from earlier species. With DNA and proteins, we still do not know what came before. The resolution may lie in molecules we have never seen, or in chemistries that no longer exist on this planet. That uncertainty makes the paradox both frustrating and inspiring. And perhaps that is the lesson to take away. The paradox of proteins and DNA is not a dead end, but a challenge, pointing us toward the need for creativity in science. If life today rests on a system that cannot logically have sprung into existence fully formed, then our task is to imagine what simpler systems might have bridged the gap. Each new experiment in prebiotic chemistry, each discovery of a molecule that can both store information and catalyze reactions, is a step toward untangling the riddle. But until we find that missing link, we are left staring at the locked door, knowing that behind it lies the origin of everything alive. And the haunting question remains, if instructions and machines depend so utterly on each other, what strange middle ground did the universe invent to get past that deadlock? Somewhere in the silence of the early Earth, there must have been a molecule or a set of reactions that broke the circle. Without it, life as we know it could never have begun. The fact that we are here proves that such a solution existed. But what it was, and whether it could happen again elsewhere, is a mystery that humbles even the most confident science. Could one molecule have done it all? That was the thought that emerged when scientists kept stumbling over the paradox of DNA and proteins. If information storage and catalytic function seemed locked in a chicken and egg loop, maybe the answer lay not in separating those roles, but in finding a molecule that could plausibly perform both. This is where RNA entered the stage as the first serious candidate for life's starting point. Unlike DNA, RNA is not just a storage device. It is chemically more reactive, less stable, and capable of folding into shapes that allow it to act like a primitive enzyme. Unlike proteins, it carries a built-in language that can encode sequences, functioning as a template for inheritance. For decades now, researchers have turned over this idea. Perhaps before DNA and proteins, there was an RNA world. The concept sounds deceptively neat. One molecule to rule them all, one bridge to span the paradox. But arriving at the hypothesis required centuries of progress in molecular biology, and testing it has required decades of painstaking experiments. To see why RNA was seen as a credible contender, it helps to step back to its structure. RNA, or ribonucleic acid, is made of 4 nucleotides, similar to those in DNA but with a key difference. The sugar backbone is ribose, not deoxyribose, and one of the bases is uracil instead of thymine. This makes RNA more flexible and chemically versatile. It can form double strands like DNA, but also loop back on itself to create complex three-dimensional structures. These folded forms allow RNA to act as catalysts, known as ribozymes, which can cut and splice other RNA molecules or even help assemble amino acids into chains. In today's cells, ribozymes still exist, tucked away at the heart of the ribosome, the machine that makes proteins. That survival is often cited as a relic of an earlier era when RNA did most of the work. Experiments beginning in the late 20th century demonstrated that RNA could indeed act like a primitive enzyme. In the laboratory, researchers discovered ribozymes capable of catalyzing chemical reactions, including the copying of short stretches of RNA itself. While no one has yet built an RNA molecule able to faithfully replicate its own full sequence, these glimpses suggested the idea was not entirely fanciful. If RNA can both store instructions and act on them, then it might have been sufficient to kickstart molecular evolution. One strand could copy pieces of itself, with errors creating variation. Natural selection could, in theory, act at this molecular scale, favouring more efficient replicators. That process would not yet be life as we know it, but it would be the seed of evolution. One strength of the RNA world idea is that it directly addresses the chicken and egg paradox. If RNA came first, then DNA and proteins are later refinements. DNA may have taken over as the more stable archive of information, while proteins took over as the more versatile catalysts. RNA remained in the middle, its role reduced but still essential in processes like protein synthesis. From this perspective, modern biology preserves a memory of its own origin, with RNA still bridging the two other molecules. That narrative has an elegant simplicity, which is why it remains one of the most discussed hypotheses for the origin of life. But simplicity should not be mistaken for certainty. For every experiment that shows RNA can do more than we expected, there are problems that remain unsolved. The first is the difficulty of making RNA in the first place. Its components, the nucleotides, do not form easily under prebiotic conditions. Early chemists struggled to imagine a plausible path from simple molecules to full nucleotides on the early Earth. More recently, some progress has been made in showing that certain chemical pathways could produce the building blocks of RNA under conditions thought to resemble the young planet. Yet even then, assembling those building blocks into long functional strands is a non-trivial leap. The stability of RNA is another issue. It tends to degrade quickly, especially in water, which raises the question of how it could persist long enough to drive sustained evolution. Despite those challenges, the RNA world hypothesis has the advantage of being experimentally testable. In laboratories around the world, researchers are attempting to evolve ribozymes that can copy themselves with increasing fidelity. Progress is incremental, but each new result makes the idea feel less speculative. Some ribozymes have been shown to join nucleotides together, others to catalyze reactions essential for replication. The picture that emerges is not of a single miraculous molecule, but of a diverse population of RNAs, each carrying out small tasks. Together they might have formed a community of cooperating molecules, exchanging pieces of themselves, and gradually improving their ability to survive and replicate. That image is humbling. It suggests that before life was cellular, it may have been a restless crowd of molecules, bumping into one another, some breaking apart, others forming alliances. In that noisy chemical soup, RNA might have stood out as uniquely capable of keeping both memory and function alive. It is not difficult to imagine the first fragile cycles of replication, with strands of RNA making crude copies, riddled with mistakes, yet slowly learning, through the blind filter of selection, to persist a little longer, to copy a little better. From such humble beginnings, the path to life as we know it could in principle be traced. Yet we must also admit what we do not know. No one has discovered a fossil of the RNA world. There are no rocks from 4 billion years ago bearing the imprint of naked strands. All we have are hints, circumstantial evidence, and the logic of molecular biology. The ribosome, with its RNA core, whispers of an earlier age. Laboratory ribozymes hint at what might be possible. But the full picture remains hidden. It is entirely possible that RNA was not the first, or that it played only a transitional role, or that life arose through chemistries now lost to time. The RNA world is a hypothesis, not a proven chapter of history. This uncertainty is not a flaw, but a reminder. It keeps science grounded in humility. It reminds us that neat stories can be comforting, but are not always true. The RNA world hypothesis is attractive precisely because it seems to resolve a paradox, but that does not guarantee it was the path taken. As scientists, the task is to test, to probe, to push against the limits of what molecules can do. The story may yet turn out to be stranger than the neat RNA first scenario. Even so, the idea leaves us with a haunting question. If RNA could, in principle, perform both roles, carrying information and catalyzing chemistry, then why did it give way? Why, once DNA and proteins entered the scene, did RNA retreat into supporting roles? Was it inevitable that life would evolve toward greater specialization? Or could there be worlds where RNA never ceded its throne, where strange ribozyme-driven organisms still dominate? We do not know. But asking the question stretches our imagination and reminds us that life is not bound to follow the script we see today. In the end, the RNA world is a story of possibility. It may be right, it may be wrong, but it gives us a concrete way to imagine a bridge across the paradox. Could one molecule have done it all? Perhaps it did, if only for a fleeting era on a restless young Earth. Or perhaps it tried and failed, leaving only traces in the biology we know. Either way, the fact that RNA sits at the heart of life today is a clue worth following. And the silence of that early world leaves us with the unsettling thought, maybe the first living things were not cells at all, but strands of RNA whispering to one another across the surface of a barren planet. What good is replication if the molecules just wash away? That question has hovered over every discussion of life's earliest chemistry. You can imagine a strand of RNA successfully making a crude copy of itself, a minor miracle by any standard, only to be carried off by a current, diluted in an ocean of unhelpful molecules, or broken apart by the constant motion of water. Without some kind of boundary, without a way of concentrating those fragile threads, the whole story would be over before it began. Molecules on their own can achieve surprising things, but evolution needs persistence. It needs a place where chemistry can build on itself, where errors can accumulate into novelty rather than simply vanish. The problem is sometimes called the dilution problem. Oceans are vast. Even if the early Earth was full of amino acids, nucleotides, and sugars drifting in solution, the chances of the right molecules repeatedly bumping into each other were slim. A single strand of RNA floating alone in seawater is like a book whose pages are scattered across the wind. It cannot hold its shape, it cannot interact with others in any stable way, and it cannot reliably reproduce. In chemistry, concentration is power. Most reactions that matter in biology today happen inside cells, in spaces where molecules are forced into proximity. Without that, even promising molecules remain little more than chemical debris. Laboratory experiments have underscored this problem. When scientists create ribozymes and place them in test tubes, they can sometimes coax them into copying parts of themselves. But success requires carefully controlled conditions, high concentrations of building blocks, and the absence of destructive forces. The natural Earth was not so cooperative. Waves crashed, tides shifted, evaporation dried pools only to have them filled again. Ultraviolet light from the young sun bombarded the surface with enough energy to break chemical bonds. Even the heat of the planet's crust could destroy delicate structures. In such an environment, molecules without shelter would have been endlessly made and endlessly destroyed. A cycle without progress. This is why the notion of boxes became essential. A box, in this context, simply means some kind of compartment that could trap molecules together, concentrate them, and shield them from the wider chaos. The box did not need to be perfect. It did not need to be alive. It just needed to hold. It could be a droplet of lipid, a bubble of oil-like molecules suspended in water. It could be a tiny pocket in porous rock where water circulated slowly. It could even be ice, forming thin films that squeezed molecules into closer quarters. What mattered was not the specific material, but the principle. Chemistry that is contained can accumulate. Chemistry that is scattered is erased. Imagine the difference between a word whispered into an empty valley and a word spoken inside a cave. The first vanishes into air, lost in distance. The second reverberates, echoing off walls, repeating itself until the sound fades. A A compartment works the same way for molecules. It allows interactions to echo, to repeat, to build momentum. Without that, no amount of promising chemistry would survive long enough to be shaped by natural selection. This fragility was not just about dilution, it was about vulnerability. RNA is not a sturdy molecule. Its bonds are weak enough that stray energy from sunlight or heat can sever them. Its tendency to fold back on itself, while useful for forming shapes, also makes it prone to breaking. In an open environment, destruction would outpace replication. A box offers not only concentration but protection. Even the thinnest membrane can slow the rate at which damaging factors reach the interior. A compartment acts like an umbrella against the rain. It does not stop the storm, but it gives the chemistry beneath a fighting chance. It is worth pausing on how radical this requirement is. When we think about life today, we see cells as the basic unit. Every living thing is boxed, whether a bacterium or a whale. But in the earliest days, before biology had fully begun, the need for boundaries was already present. It was not an optional feature added later for convenience. It was built into the very possibility of persistence. Life is chemistry boxed in. Without walls, there is no memory, no lineage, no future. Some researchers have tried to imagine how long naked molecules could have persisted before compartments appeared. The answer is probably measured in moments, not millennia. A naked replicator could exist, but it could not dominate. It could spark, but it could not burn. To transition from fleeting sparks to a fire, molecules needed somewhere to cluster. This insight shifts the origin of life problem from being solely about chemistry to being equally about architecture. Molecules are not enough. There must also be space, boundary, and shelter. The beauty of this idea is that nature does not need to invent boxes from scratch. Simple physical processes can create compartments spontaneously. Shake oil and water together and droplets form. Freeze water and thin channels between ice crystals concentrate solutes. Dry a puddle and molecules are forced into close contact as water retreats. The early Earth would have provided countless such opportunities, and some of them may have been just enough to let fragile RNA linger. Yet opportunity is not certainty. The haunting question is how many times these proto-boxes must have formed and failed before one finally endured. The requirement for compartments also reframes what we mean by the first life. Was it the molecule that could copy itself? Or was it the first cluster of molecules inside a protective bubble? Or was it only when both came together, replication inside a box, that we should consider life as having truly begun? These are not just semantic questions. They reflect a deeper truth. Life is not just chemistry, but chemistry in context. The context is the box. Without it, replication is noise. With it, replication becomes memory. And yet, even this framing leaves us uncertain. No one has found a direct fossil of the first compartments. We cannot point to a rock and say, here, in this bubble, life began. What we have are experiments, logic, and the persistent survival of cells as proof that boxes mattered. Every bacterium on Earth today is a living testimony that the box worked. The fragility problem was solved somehow. But the details remain hidden, scattered by billions of years of tectonics, erosion, and change. So we are left with the recognition that fragility was both a curse and a gift. It threatened to erase every attempt at progress, but it also demanded a solution that gave rise to one of the life's most fundamental features, the cell. Out of necessity came structure. Out of vulnerability came resilience. The molecules needed boxes, and the boxes became bodies. That realization leads us to another haunting thought. If compartments were required here, would they be required everywhere? Could life exist without them, in some alien ocean or atmosphere? Or is the box a universal prerequisite? If so, then perhaps the search for life beyond Earth should focus as much on boundaries as on molecules. We may not yet know how life began here, but we know this: no chemistry, however promising, can survive forever in the open. Replication without shelter is just a story that ends too soon. The search for how the first compartments might have formed has become its own quiet branch of science. One of the most compelling demonstrations is deceptively simple. Mix a handful of fatty acids in water, and without any guiding hand they spontaneously arrange themselves into bubbles. This happens because the molecules have two personalities stitched into one body. One end is drawn to water, the other repelled by it. Put them together, and they resolve their internal tension by curling into spheres, hiding their water-hating ends inside and exposing their water-loving ends to the surrounding liquid. The result is a vesicle, a fragile translucent bubble only micrometers across, yet astonishingly similar in architecture to the membranes that enclose every cell alive today. The implication is difficult to ignore. If simple fatty acids can do this under laboratory conditions, then on a planet covered in diverse carbon-rich chemistry, billions of tiny bubbles might have formed without effort. But vesicles are not the only kind of boxes. Minerals can serve as boxes too. Think of porous volcanic rock, riddled with microscopic chambers left behind by cooling gas. Within such chambers, fluids circulate slowly, molecules accumulate, and energy gradients form across mineral walls. A strand of RNA finding itself in such a pore would be less exposed to dilution, less likely to drift away. It would be, in effect, inside a naturally occurring laboratory flask. Studies of clays and other silicates have shown that they can not only trap nucleotides, but also catalyze their joining into longer chains. The walls of the box do more than contain. They can actively guide the chemistry within. Even ice, often dismissed as an enemy of life, may have been an early ally. When water freezes, it does not trap all solutes evenly. Instead, salts, sugars, and nucleotides are excluded from the growing ice crystals and squeezed into narrow veins of concentrated liquid between them. These veins act like miniature test tubes, bringing molecules together in close quarters. Paradoxically, freezing may have been a way to concentrate life's ingredients in a thin protective film, slowing destructive reactions while allowing constructive ones to proceed. To imagine life's chemistry beginning not in a warm pond but in the crevices of ice is counterintuitive, but it reflects how fragile molecules often require environments we would not first suspect. Laboratory experiments have tested these ideas in surprising ways. When fatty acid vesicles are dried and then rehydrated, they tend to divide into smaller vesicles, mimicking the way cells grow and split. When nucleotides are supplied to vesicles, some manage to slip inside, suggesting that an RNA world sheltered within bubbles is not impossible. When scientists combine simple amino acids and lipids, they find that membranes become more robust, hinting that the earliest compartments may have been chimeras of different chemistries, gradually stabilizing themselves through trial and error. Each of these results is modest on its own, but together they point toward a principle. Compartments are not just possible, they are practically unavoidable under the right conditions. There is also the curious phenomenon of 𝐓𝐀𝐒𝐏𝐻𝐒, droplets formed when certain organic molecules phase separate from water, much like oil droplets forming in vinegar. These droplets can trap other molecules inside and create microenvironments with different chemical rules than the outside world. Alexander Aperin, the Russian biochemist who first popularized the primordial soup concept, was fascinated by 𝐓𝐶𝐂𝐻𝐒s in the early 20th century. Though we now know they are not alive, they show how simple chemistry can organize itself into bounded structures without any guiding hand. In them, one can glimpse how nature might have rehearsed the idea of cells before true cells existed. What unites all these possibilities of vesicles, pores, ice films, 𝐓𝐶𝐂𝐻𝐒s is not their specific chemistry, but the fact that they create pockets of persistence. The open ocean is too vast, too destructive, too impermanent, but in small spaces, concentrations rise, reactions repeat, and fragile molecules are given time to matter. Evolution does not need perfection, it only needs persistence. Once a few molecules survived long enough to replicate and improve, the relentless sieve of natural selection could begin to favour those arrangements that held together. From this perspective, life's emergence looks less like a miraculous spark and more like a patient filtering of countless fragile beginnings. And yet, the haunting question remains. Why did only one version of this boxed chemistry survive? If early Earth offered endless compartments, bubbles, pores, ice, 𝐓𝐶𝐂𝐻𝐒s, why is life today based on membranes made of phospholipids enclosing water-based interiors? Did other compartments exist but fail, their chemistries too unstable to compete? Were there once alternative boxes carrying alternative molecules, different paths toward life that blinked out and left no trace? The silence of deep time gives no answer, but the question lingers. To recognize the fragility problem is to see life as more improbable and more inevitable at the same time. Improbable, because any single strand of RNA or any single bubble of fatty acids was almost certain to fail. Inevitable, because the Earth offered so many billions of chances for failure that eventually persistence had to win. The boxes formed, most vanished, but one lineage endured. Every cell today is a descendant of that improbable survivor. The walls that enclose our own cells are a living reminder that fragility was once the greatest threat, and containment was the first solution. How do molecules build their own walls? It sounds absurd, like asking how sand might build a castle without hands, or how drops of oil might invent a jar to live in. And yet, fatty acids appear to do just that. Long before there were cells with complex membranes and machinery, there was a more primitive chemistry that stumbled into something both simple and profound: self-assembled compartments. These early structures are not life as we know it, but they represent one of the most essential steps toward it. Because without walls, molecules diffuse into nothingness. Without borders, there is no persistence. And without persistence, there is no possibility for evolution to begin its patient, grinding work. Fatty acids are peculiar molecules, halfway between friendliness and hostility toward water. At one end, they carry a polar head that is drawn to water like a magnet. At the other end, they trail a hydrocarbon tail that recoils from water like oil does from vinegar. This duality is not exotic, it is common. Fatty acids form in many natural settings, from simple chemical reactions in the atmosphere to carbon-rich molecules altered in the heat and pressure of early Earth's crust, and even within meteorites that fell to the planet's surface. The odd thing is what they do once they find themselves floating in water. They cannot remain scattered as individuals. Instead, their chemical personalities drive them to gather, to huddle, to organize. Tails hide from water while heads face it, and the result is a spontaneous structure. Depending on conditions, these can be micelles, small spherical clusters with tails tucked inside, or vesicles, hollow spheres with a watery interior. The chemistry compels the architecture, no guiding hand required. What makes vesicles special is that they create an inside and an outside. In the most minimal sense, they make a boundary. Inside the thin film of fatty acids is a pocket of water cut off from the larger ocean. For any strand of RNA or any reactive molecule caught inside, this is no small matter. It is safety from dilution, a stable environment where interactions repeat. In laboratory experiments, when fatty acids are simply shaken into water, vesicles appear. When dried and re-wetted, they grow and divide. When nutrients are supplied, they can take in nucleotides and other molecules, albeit clumsily. No one claims these are alive, but the fact that bubbles can self-assemble and behave in ways faintly reminiscent of growth and division suggests that protocells are not a leap into fantasy. They are a natural tendency of certain molecules, an emergent feature of chemistry itself. To put this in context, think of early Earth around 3,900,000,000 years ago. Oceans stretched vast and young, salted with minerals leached from volcanic rocks, stirred by tides and meteor impacts, warmed in places by hydrothermal activity. In these waters, organic molecules delivered by meteorites or forged by atmospheric reactions mingled with whatever chemistry the crust provided. The ocean was no uniform soup. It was patchy, gradient-rich, full of niches. In some patches, fatty acids might reach the right concentration to form vesicles spontaneously. In others, drying lagoons might concentrate them further, and upon re-wetting, entire populations of vesicles could form at once. Each vesicle, a tiny micro-world, enclosed whatever chemistry chance had placed inside. Some contained nothing of note. Some perhaps enclosed a few reactive molecules, maybe even fragments of RNA. The vast majority vanished without consequence. But a handful may have lingered long enough to allow something novel to happen within. Experiments have shown that fatty acid vesicles are surprisingly dynamic. Unlike modern phospholipid membranes, which are stable and tightly sealed, fatty acid membranes are leaky and prone to turnover. This fragility can be a strength. Molecules like nucleotides, which are the building blocks of RNA, can slip across these primitive walls more easily than they could across modern membranes. This means protocells could feed themselves passively, without requiring protein channels or pumps, which of course did not exist yet. The very looseness of the walls may have been what allowed early protocells to sustain chemistry inside. Stability was not yet the goal. Access and exchange mattered more. Another intriguing property is how vesicles can grow. If fatty acids are supplied from the outside, the vesicles naturally incorporate them into their walls, becoming larger and more irregular. Under stress, such as cycles of heating and cooling, they can split into smaller vesicles. In the laboratory, this looks eerily like cell division, though it is nothing more than physics. Still, it demonstrates a path by which compartments could persist across cycles of growth and fragmentation. Imagine countless generations of vesicles swelling and dividing, not guided by genomes, not alive in the sense we know, but providing continuity and variation nonetheless. Within this churn, those vesicles that happened to enclose chemistry that helped stabilize them, say, RNA strands that reinforced the membrane or catalyzed the production of more fatty acids, would have had an advantage. This is where natural selection could begin, not with organisms, but with protocells competing for persistence. It is tempting to see protocells as inevitable. After all, given the right molecules, they seem to assemble themselves. But inevitability is a dangerous word in science. We must acknowledge the uncertainty. Fatty acids may have been abundant or they may have been rare. They may have formed easily in the atmosphere or arrived on meteorites, or they may have required more complex pathways that were not universal. Even if they formed, their stability in early oceans, rich in salts and metals, might have been poor. Some studies suggest fatty acid vesicles collapse in salty conditions like those of modern seawater, though others propose that certain minerals could have stabilized them. The truth is, we cannot reconstruct the exact chemistry of those ancient oceans, and therefore we cannot be certain how common or robust protocells were. Yet, even if protocells were fragile and fleeting, time was on their side. Over hundreds of millions of years, countless cycles of formation and destruction could have occurred. In shallow pools, in volcanic ponds, in ice veins, in porous rocks, fatty acids may have repeatedly formed vesicles, enclosed random chemistry, and disintegrated. Most would have left no trace. But perhaps once in a while, by extraordinary coincidence, the contents of a vesicle included molecules that helped it endure just a little longer. Those few extra moments could have made all the difference, allowing chemistry to proceed toward complexity. Life does not require frequent success. It requires persistence through rare success. The very idea of protocells carries with it a philosophical weight. It suggests that the difference between non-life and life is not an unbridgeable chasm, but a gradient. At one end, mere molecules bouncing in solution. At the other, compartments that grow, divide, and compete. The boundary is blurry, and protocells dwell right in that ambiguity. They are not alive, but they are more than random. They are organized, bounded, persistent. In them we glimpse a middle ground where chance and necessity meet, where chemistry rehearses biology. What remains unanswered is why only one path succeeded. Were there once multiple kinds of protocells experimenting across Earth's surface? Could some have been based on entirely different lipids, or even non-lipid compartments like mineral enclosures? Did these alternative boxes thrive for a while, before vanishing into extinction without fossils to mark their presence? If so, then the protocells we study today are not the only story, but simply the one that happened to lead to us. The haunting question that lingers after considering fatty acids and protocells is this: was life's architecture dictated by inevitability, or was it a fragile accident that survived against overwhelming odds? If inevitability, then wherever fatty acids and water meet in the cosmos, compartments may form and prepare the stage for life. If accident, then our existence may hinge on one improbable bubble that refused to collapse. Both possibilities are humbling. Both remind us that walls, which seem so ordinary, may have been the first great invention of chemistry on the road to biology. Life needs energy. That is almost the only thing everyone agrees on. Without a constant flow of usable energy, no molecule can stay organized, no reaction can keep cycling, no fragile protocell can avoid dissolving back into chaos. But before the invention of photosynthesis, before organisms learned to capture sunlight and turn it into sugars, where did that energy come from? The Earth 4 billion years ago was a restless and violent world, and it is here, in that seeming hostility, that scientists now look for the sparks and gradients that may have powered the very first steps toward metabolism. The puzzle is simple to state, but difficult to solve. How can chemical systems sustain themselves long enough to climb the ladder from random reactions to the beginnings of life? When we picture energy today, we imagine food, calories, fuels, or the sun's rays on leaves. But all of these are late inventions. Energy in its most primitive form is the imbalance of charges and the transfer of electrons. A stone rolling downhill releases gravitational energy because it is moving from a higher state to a lower one. Chemistry is no different. Electrons shift from one molecule to another, releasing energy that can be captured. In the modern cell, these electron transfers are organized into elegant cascades of enzymes, with each step carefully tuned. But there must have been a time before enzymes when the raw world itself provided gradients and imbalances. Without those, nothing could have started. One of the most intriguing proposals is that early life exploited proton gradients. Modern cells use proton gradients everywhere. Mitochondria, the energy factories of our bodies, rely on pumping protons across membranes and then letting them flow back in, capturing their movement to drive the synthesis of ATP, the universal energy currency of life. This is so universal across all known life that some scientists argue it must have roots deep in the very origin of life. The challenge is imagining how such gradients could exist before cells had the machinery to make them. One answer lies not within the cells but outside them, in the rocks and waters of early Earth. Alkaline hydrothermal vents, which still exist today in certain parts of the ocean floor, create precisely the kind of natural proton gradients that early life might have needed. These vents form when seawater seeps into cracks in the ocean crust, reacts with minerals, and emerges as warm alkaline fluids rich in hydrogen and other reduced molecules. The surrounding seawater is more acidic and full of carbon dioxide. At the boundary between these two fluids, you have a natural battery, one side rich in donors, the other rich in acceptors, with a physical barrier of mineral pores in between. Across those pores, a proton gradient exists for free. Molecules that happen to lodge themselves in such environments could, in theory, tap into that energy without needing to build the machinery themselves. This is where the theory known as metabolism first gains its foothold. The idea is that before there were genes, before there was replication, there were cycles of reactions powered by energy imbalances in the environment. If life's ancestor began in these alkaline vent systems, then it did not have to invent proton gradients. It borrowed them from geology. Minerals like iron sulfides could have acted as crude catalysts, helping electrons move along their journeys. Hydrogen from vent fluids and carbon dioxide from seawater could have combined, under the right conditions, to make small organic molecules, formate, acetate, maybe even pyruvate. Each of these is a step along pathways still central to modern metabolism. If this sounds speculative, it is. But it is speculation tied to evidence. Laboratory experiments have shown that under vent-like conditions, with iron-sulfur minerals present, some of these small organic molecules can indeed form spontaneously. Not in abundance and not always reliably, but enough to suggest plausibility. It is a humbling reminder that metabolism, which seems like an invention of life, may instead have begun as a gift from Earth's geochemistry. Cells later internalized and perfected these flows of energy, but they may not have created them from scratch. Another concept in this framework is redox chemistry, the push and pull of reduction and oxidation. On the early Earth, there was no oxygen atmosphere, but there were plenty of other electron acceptors and donors. Hydrogen was abundant in vent fluids. Carbon dioxide was abundant in the ocean and atmosphere. The reaction between these two is not easy, but with minerals to help it can proceed. Once molecules like acetate or formate existed, they could feed into cycles that resembled primitive versions of the Krebs cycle, which all modern life uses to generate energy and building blocks. The critical point is that energy flows through electron transfers, and these transfers were available in the environment long before enzymes evolved. It is worth pausing here to consider just how strange and counterintuitive this is. We are used to thinking of life as the innovator, the clever system that figures out how to use energy sources. But in this view, life is less an inventor and more an opportunist. The energy flows were already there, written into the chemistry of the Earth's crust meeting the ocean. Life's first task was not to create them, but to capture them, to build enough structure to ride the gradients rather than be dissolved by them. In this sense, life's beginning looks less like a miraculous invention, and more like a slow co-option of natural flows. Of course, this does not answer everything. Proton gradients are useful, but how were they captured by fragile protocells with leaky fatty acid walls? Some models propose that mineral pores at vent chimneys acted as natural compartments, concentrating molecules while maintaining access to the gradient across the mineral walls. In this model, protocells began not as free-floating bubbles, but as communities of molecules trapped in tiny rock chambers. Over time, those that managed to internalize the gradient, perhaps by developing rudimentary membranes, could break free. The world of vents thus provides not only energy but also structure, a ready-made laboratory for prebiotic chemistry. Critics point out that this picture is elegant but not proven. Hydrothermal vents today are complex ecosystems teeming with modern life, but we do not see new life arising in them. Some argue that the conditions 4 billion years ago were unique, with different ocean chemistry and higher energy fluxes. Others worry that vent chemistry might not produce enough variety of organics to bootstrap metabolism. And then there is the haunting possibility that while vents provide one plausible setting, there may have been many, and we may never know which one actually seeded life. Shallow ponds with cycles of drying and wetting, volcanic hot springs on land, even ice-covered oceans, all have been proposed. The vent model is compelling, but not exclusive. Still, the focus on energy remains a crucial lesson. No matter where life began, it had to find a way to sustain itself against entropy. The idea that proton gradients and redox flows were harnessed before enzymes existed shifts our perspective. It suggests that the very logic of bioenergetics is older than biology itself. The way modern cells make ATP is not just a biological trick, but perhaps an inheritance from the rocks and waters of a young Earth. So the haunting question becomes this: was life inevitable once the right gradients appeared, or was it a fragile accident that seized a narrow opportunity before the gradients faded? If inevitability, then wherever similar vents bubble on icy moons or distant exoplanets, we might expect life to arise again, not as a miracle but as a natural outcome of physics and chemistry. If accident, then our existence rests on a lucky match of vent, mineral and molecule, a lottery ticket won 4 billion years ago that may never be drawn again. We cannot yet say. But in asking, we remind ourselves that before enzymes, before genes, before cells, there was energy. And it is in that restless flow of electrons and protons that the faint heartbeat of life may have first stirred. Was life born in the dark pressure of the ocean depths, or did it first stir in the flickering warmth of shallow pools? That is the riddle that divides origin of life science into two grand camps. Each side points to an environment on early Earth that could, in theory, have offered the right conditions for complex chemistry to take a step toward biology. One vision takes us far beneath the waves, into the labyrinthine mineral towers of hydrothermal vents. The other vision lifts us up into the sunlight, into shallow ponds on volcanic landscapes where water evaporated, concentrated and refilled in endless cycles. These are not idle choices. Each environment offers different energy sources, different chemistries, and different answers to the question of whether life is a cosmic inevitability or a fragile accident. The story of the warm little pond begins with Charles Darwin himself. In the year 1871, in a private letter, he wrote of the possibility that life could have originated in some warm little pond, with all sorts of ammonia and phosphoric salts, light, heat, electricity. It was a throwaway thought, more musing than theory, but it set the imagination of later scientists ablaze. The idea appealed because it was simple. A small body of water, heated by the sun or volcanic activity, rich in dissolved minerals, could concentrate organic molecules and allow them to interact. Evaporation could dry the pond, leaving thin films where reactions sped up. Rain could return, mixing the products. Cycles of wetting and drying became a natural chemistry engine. Hydrothermal vents, by contrast, emerged in the scientific imagination only much later, after their discovery in the 1970s. These vents are places where seawater percolates through the crust, reacts with hot rock, and re-emerges carrying minerals and gases. Towering chimneys of iron and sulphur rise from the seabed, and within their porous walls lie countless tiny chambers. For origin of life theorists, these chambers became a natural laboratory, offering enclosed spaces, steep chemical gradients, and mineral catalysts. Unlike Darwin's ponds, which depend on the vagaries of weather, vents provide continuous energy and chemical disequilibrium. They are steady, geologically powered batteries. Both settings have experimental support and both have difficulties. Take the ponds first. Laboratory work has shown that cycles of drying and rehydration can indeed promote the formation of long chains from simple molecules. Amino acids can link into short peptides. Nucleotides can polymerize into RNA-like chains more efficiently on mineral surfaces when water levels fluctuate. These results give substance to Darwin's old speculation. Ponds also offer sunlight, which can drive reactions that do not occur in the dark. Ultraviolet radiation, harsh though it is, may have helped to energize precursors of nucleotides. In this light, ponds look like natural workshops, small enough to concentrate molecules, dynamic enough to promote complexity. Yet ponds also pose problems. Their very openness makes them vulnerable. Any promising chemistry could be diluted away into the larger environment. Molecules formed during one cycle might be destroyed in the next. Ultraviolet light can create, but it also destroys, breaking delicate bonds as quickly as it forms them. And there is the issue of stability. How often would such ponds exist on the early Earth, and for how long would they persist before drying completely or being washed away by floods? For life to emerge, you need not just chemistry, but continuity. Some argue that warm little ponds may have been too fleeting to nurture the long, improbable chain of events that led to the first cells. Now consider the vents. Experiments under vent-like conditions have demonstrated that minerals such as iron sulfides can catalyze the formation of small organic molecules from simple gases like carbon dioxide and hydrogen. In alkaline vents, natural proton gradients exist across thin mineral walls, reminiscent of the proton gradients used by all modern life to generate energy. This has inspired the theory that early metabolisms could have arisen by directly exploiting these natural gradients. Instead of the chaotic cycling of ponds, vents offer a steady supply of energy and a structured environment where molecules are not easily washed away. But the vents have their own challenges. Temperatures near vent outlets can be extremely high, enough to denature fragile organic molecules. While cooler zones exist within vent structures, it is not clear whether molecules could remain in the right places long enough to evolve complexity. The vastness of the ocean is also a problem. Any products that escaped the vent environment could be diluted to irrelevance. And although mineral pores offer confinement, they are not membranes. To transition from vent chemistry to free-living protocells requires a leap that is still poorly understood. So which setting is more plausible? The truth is that no one knows. Some researchers champion ponds because they allow for cycles of concentration, because they are easier to reconcile with laboratory demonstrations of polymer formation, and because they resonate with Darwin's simple vision. Others argue fiercely for vents, pointing to the universality of proton gradients in modern biology and the continuity of energy flows that vents uniquely provide. The debate is not merely academic. It reflects two different philosophies of life's origin. Ponds suggest that life began in fits and starts, in fragile surface environments, making the leap from chemistry to biology under the occasional favour of chance. Vents suggest that life arose from continuity, from the steady march of geochemistry, making life less a fluke and more a geologically inevitable outcome. There is also the possibility that both played roles. Molecules synthesized in vent environments might have been transported to the surface, where ponds concentrated and polymerized them further. Or vice versa. Surface chemistry might have generated precursors that were later stabilized and integrated in vent conditions. The early Earth was a mosaic of environments, from volcanic islands with steaming pools to vast oceans with vent fields, and it would be unwise to assume that life's origin was confined to only one setting. Still, in the scientific literature, ponds and vents stand as archetypes, each with its camp of supporters, each providing a lens through which to interpret experimental results. In weighing them, it is essential to remember humility. No matter how elegant a model looks in hindsight, we cannot run the clock back 4 billion years. The conditions then were not identical to anything we can replicate now. The oceans had different chemistries, the atmosphere was different, the surface was bombarded by impacts. Our laboratory experiments are at best analogues, glimpses into what might have been, and this makes the haunting question all the sharper. Is the debate between vents and ponds even the right way to frame the problem? Perhaps life required both. Perhaps it required something else entirely that we have not yet imagined. For now, the debate remains unresolved but productive. Each side forces the other to sharpen its arguments and test its assumptions. Each inspires new experiments, whether in simulating vent conditions with mineral reactors or recreating pond-like cycles of wetting and drying in the lab. And through this debate, we are reminded of the vastness of the unknown. Was life born in the black smokers of the ocean floor, or in the sunlit ripples of shallow ponds? The answer, if we ever reach it, will tell us not only where we come from, but how likely it is that life could arise elsewhere. For if life begins in warm ponds, then planets with land and shallow water may be favoured. If life begins in vents, then icy moons with subsurface oceans might be equally fertile. The choice between vents and ponds is, in the end, a choice between different universes of possibility. And so we are left with the unsettling thought, what if the place we imagine as home to life's origin was never the only option? What if the instructions for life were not written here at all, but instead rained down from the sky? It is a strange thought, that the seeds of biology might have been delivered to Earth already formed, packaged inside stones cast adrift from elsewhere in the cosmos. Yet for as long as we have been puzzling over the mystery of life's beginning, we have been forced to confront the possibility that Earth was not entirely self-sufficient. During the period we call the Late Heavy Bombardment, roughly between 4.1 and 3.8 billion years ago, our planet was struck again and again by asteroids, comets, and other debris left over from the violent birth of the solar system. For Earth, this was both a time of devastation and a time of delivery. Each impact carried the potential to sterilize whole regions of the surface, yet each also brought with it cargo, minerals, water, and most intriguingly, organic molecules. The first hint that extraterrestrial rocks could carry such things came much later, when scientists began studying meteorites that had fallen in recent centuries. Among the most famous was the Murchison meteorite, which fell in Australia in the year 1969. This single stone turned out to be rich in carbon compounds, including amino acids, purines, and other organic molecules. Its chemistry revealed that complex organics can form in space, in environments far removed from Earth. And Murchison was not unique. Other carbonaceous chondrites, fragments of primitive asteroids, have yielded similar results. They preserve in their interiors a record of reactions that took place in the cold darkness of interstellar space, and in the warm interiors of small bodies heated by radioactive decay. These meteorites show that organic chemistry is not a rare or fragile process. On the contrary, it seems to unfold wherever the right conditions exist, in clouds of dust between the stars, in icy comets orbiting far from the sun, in asteroids with liquid water locked within their pores. Space, for all its hostility, appears to be fertile ground for simple molecules that resemble the bricks of life. The lesson is sobering. If such chemistry occurs beyond Earth, then our planet was almost certainly bombarded with these molecules throughout its early history. The question is not whether organics arrived, but how important they were to life's origin. Some scientists argue that these deliveries may have been decisive. Perhaps the early Earth, hot and hostile as it was, would have struggled to synthesize certain fragile molecules on its own. By contrast, the gentle chemistry of interstellar ice could build sugars, nucleobases, and other complex compounds shielded within dust grains. Comets and meteorites then acted as couriers, carrying these products across the void and releasing them onto Earth's surface. In this view, the recipe for life was written in the stars long before our planet cooled enough to host oceans. Others are more cautious. They point out that while meteorites contain organics, the concentrations are low and the diversity is limited. It is one thing to find amino acids or nucleobase analogues in a fragment of rock, but it is another thing entirely to imagine them building the first living system. Delivery may have supplemented Earth's own chemistry rather than replacing it. And there are questions of survival. The energy released during an impact is immense, enough to vaporize rock and boil oceans. Would fragile molecules have endured such violence, Or would they have been incinerated in the fireball? Experiments suggest that some fraction could survive, especially if buried deep within the meteorite's interior, or delivered by smaller impacts that dissipated less energy. Still, uncertainty remains. The panspermia hypothesis extends the idea further. If meteorites can carry molecules, might they not also carry life itself? Some proponents suggest that microbes could, in principle, endure ejection from a planet, travel through space protected by rock, and then seed another world upon arrival. Laboratory studies have shown that certain hardy microorganisms can indeed survive years in space, shielded from radiation. Fossilized-looking structures in meteorites have fueled speculation, though none have been universally accepted as biological. Mainstream science treats panspermia cautiously. It does not solve the problem of life's origin, but only moves it elsewhere. If life arrived here from another world, we're still left asking how it began there. And yet, the appeal of cosmic delivery persists, in part because it widens the frame. If organic molecules form readily in space, then the universe is likely littered with the raw ingredients of life. The building blocks are not rare jewels, but common dust. That realization has profound implications. It means that Earth may not be exceptional in having access to these molecules. Mars, icy moons, even distant exoplanets may have received similar deliveries. The universality of organic chemistry makes the question of life not just an earthly puzzle, but a cosmic expectation. The bombardment period on Earth was brutal, but paradoxically it may have been creative. Each impact sterilized, yes, but also enriched. Each crater was both a wound and a laboratory, a basin where water and rock and cosmic organics could mingle. In this sense, the violence of the early solar system was not only destructive but also generative. Without bombardment, Earth might have remained chemically impoverished. With it, our planet became a crucible in which local and extraterrestrial chemistries could fuse. Skeptics remind us, however, that evidence is fragmentary. Meteorites we study today fell recently, long after life was established. We cannot directly inspect the cargo of the bodies that fell 4 billion years ago. Our conclusions rest on inference, on analogues, on the extrapolation of laboratory data. It is entirely possible that meteorites contributed only a fraction of the molecules that mattered, and that Earth's own chemistry did most of the heavy lifting. The debate echoes that over vents and ponds. Was life primarily Earth-made, or did it borrow heavily from the heavens? The answer is uncertain, but the framing itself is telling. It reflects a shift from asking whether space delivered anything at all to asking how much it delivered and how significant it was. Here the haunting question emerges: what if the spark of life did not depend on where it happened, but on when? The bombardment was a finite event. It enriched Earth for a window of time and then waned. If the right chemistry had to align with the right deliveries, then life's origin may have been balanced on a razor's edge of timing. Too soon, and the planet was still too hostile. Too late, and the bombardment had faded, leaving Earth without fresh supplies. Did we owe our existence to a cosmic delivery schedule that just happened to align with Earth's own cooling? We are left with a picture at once humbling and unsettling. We know that meteorites carry organics. We know that Earth was showered with them during its formative years. We suspect that they played a role, perhaps crucial, in nudging chemistry toward biology. But we do not know whether they were the deciding factor or only an accessory. We do not know whether panspermia has ever actually occurred, or whether life is still, in the end, a local story. What we do know is that, when we look at a meteorite in a museum case, we're not just looking at a rock. We are looking at a piece of an ancient delivery system, a fragment of the cosmic mail that may have carried the first hints of life to Earth. And the question that lingers, softly but persistently, is whether those deliveries are happening elsewhere, on other worlds, right now. Can rocks think, just a little? The question sounds absurd at first because we instinctively link thought to brains, neurons and organisms. Yet in the search for life's beginnings, we must start humbler than that. Before there were organisms, there was chemistry. And before there were the vast webs of enzymes and molecules that we call metabolism, there may have been nothing more than simple reactions, catalyzed by minerals and driven by gradients of energy. Rocks cannot think in any conscious sense, but under the right conditions, they can guide and shape the flow of matter in ways that resemble the earlier steps of metabolism. To trace the origin of life, we must consider the possibility that Earth itself was the first chemist, and that life is the inheritor of patterns already tested by stone and water. Between about 3.9 and 3.5 billion years ago, the young Earth was still cooling, still unstable, but no longer the hellscape of its earliest epochs. Oceans had settled across much of the surface, hydrothermal systems pulsed with heat and minerals, and the atmosphere was rich in gases like carbon dioxide, hydrogen and methane. These were the ingredients of a restless chemical world, one where geochemistry set the stage for biology. If we ask how living metabolism began, one answer is that it did not start from scratch. Instead, it borrowed from cycles already running in the environment, cycles written not by enzymes but by rocks. One of the most studied ideas in this vein is that of mineral-driven pathways resembling the acetyl-CoA cycle, one of the core routes in modern metabolism. In today's organisms, the acetyl-CoA pathway is central to how cells process carbon, linking the breakdown of molecules to the building of new ones. It involves dozens of enzymes, each carefully tuned to channel atoms through precise steps. But the striking thing is that some of its individual reactions can occur without enzymes at all, if given the right minerals. Iron-sulfur compounds, for example, have a natural tendency to transfer electrons and to bind to carbon monoxide and carbon dioxide. In the presence of hydrogen, they can drive the reduction of carbon dioxide into simple organic molecules like formate or acetate. These are tiny, modest compounds, but they represent the basic bricks of metabolism: energy carriers, building blocks, and intermediates in carbon chemistry. Laboratory studies have shown that under simulated hydrothermal conditions, iron and nickel sulfides can indeed catalyze reactions that look like shadows of the acetyl coenzyme A pathway. Carbon dioxide dissolved in water, when exposed to these minerals and supplied with hydrogen, can be reduced to organic acids and alcohols. None of this requires enzymes or living cells. It requires only the chemistry of Earth itself. What life later perfected with proteins may have begun as a geochemical tendency. If that is true, then the first metabolism was not invented by biology but inherited from rocks. Another candidate is the iron-sulfur world hypothesis, which suggests that the surfaces of sulfide minerals could have acted like primitive metabolic scaffolds. In modern biology, iron-sulfur clusters are still essential, found in the active sites of many enzymes. Their ability to shuttle electrons makes them ideal for redox chemistry, the core of energy transfer. The idea is that before there were enzymes to hold these clusters, there were just the clusters themselves, embedded in mineral surfaces at hydrothermal vents. These surfaces could have concentrated molecules, catalyzed reactions, and set up cycles that resembled the core of metabolism. Cycles are the key word. Simple chemistry can make a molecule, but metabolism is more than synthesis. It is the coupling of reactions into repeating loops, where the output of one step becomes the input of another, sustaining itself so long as energy flows in. Could minerals have done this? Some researchers argue that yes, they could. The citric acid cycle, for instance, can be partly replicated abiotically under certain conditions, with intermediates like succinate and fumarate forming in the absence of enzymes. These reactions are inefficient and incomplete, but they hint that cycles are not uniquely biological inventions. They are patterns of matter and energy that arise whenever conditions permit. If so, then life's earliest metabolism was simply the stabilization of these patterns inside compartments. Instead of relying on scattered mineral surfaces, protocells could trap molecules and allow cycles to persist. Biology, in this view, is geochemistry that found a way to copy itself. The leap was not from nothing to complexity, but from scattered cycles to sustained cycles. Of course, not everyone agrees. Critics point out that while mineral catalysis can produce organic molecules, the yields are tiny, the conditions delicate, and the cycles fragile. It is one thing to demonstrate a single reaction in the lab, and quite another to assemble an entire pathway robust enough to sustain growth. Without enzymes, the reactions may stall, drift, or collapse. Life's metabolism is not only about possibility, but about efficiency, and efficiency may have required molecules that could evolve and refine. Rocks, for all their usefulness, cannot evolve. They can only react in the same way, again and again, yet even inefficiency has its place. In the vast oceans of early Earth, with countless hydrothermal systems and mineral-rich settings, reactions could have run continuously, producing pools of organics over millions of years. It may not matter if any single system was efficient, so long as enough of them operated simultaneously. Abundance could compensate for weakness. In this sense, life's beginnings may have been statistical. Somewhere, among countless geochemical cycles, the right sequence happened to stabilize. The question of timing is crucial. Between 3.9 and 3.5 billion years ago, evidence suggests that life was already emerging. Ancient rocks contain isotopic signatures consistent with biological activity, though interpretations remain debated. If true, then life took hold remarkably quickly after Earth became habitable. That speed suggests that the gap between geochemistry and metabolism was not insurmountable. It may even have been natural given the right setting. We can imagine the scene, of vents spewing mineral-rich fluids into an ocean, iron-sulfur minerals precipitating at the interface with seawater, tiny compartments forming within the rock. Within these spaces, hydrogen and carbon dioxide flow through, reactions spark and simple organic molecules accumulate. Some are lost, others degrade, but a few feed into repeating loops. These loops are not alive, not yet, but they embody persistence. They represent the first hints of continuity, the transformation of energy into pattern. The haunting question then is this: at what point do we call it life? If a mineral surface drives a reaction that repeats, sustaining itself so long as energy flows, is that not the skeleton of metabolism? And if metabolism is the essence of life, does that mean life began before cells, before genes, before anything that could be called an organism? Perhaps life is not something that started abruptly, but something that thickened gradually out of the background chemistry of a restless planet. We remain humble here, because the evidence is incomplete. Rocks 3.5 billion years old are rare and altered, their original chemistry overwritten by time. We cannot look directly into the crucibles where these cycles began. We can only reconstruct them in the lab, test their plausibility, and admit the gaps. Still, the parallels between mineral chemistry and modern metabolism are striking enough that we cannot dismiss them. Life's core pathways may be echoes of reactions older than life itself, written first in stone and only later in cells. So can rocks think just a little, not in any conscious sense. But they can, under the right conditions, channel matter and energy into patterns that resemble the logic of metabolism. And perhaps that is what life really is. Not a sudden spark, but the realization of possibilities already latent in the chemistry of the Earth. The unsettling implication is that if geochemistry tends naturally toward metabolism, then life may not be rare. It may be a tendency of matter itself, waiting only for the right rocks, the right oceans, and the right flows of energy. Are we really looking at the oldest life, or just weird rocks? That question has haunted geology and paleontology for more than a century, and it still lingers today. If we are to claim that we have seen the first fossils, we must tread carefully. Fossils are the preserved remains or traces of past life. But in the world of 3.5 billion years ago, the line between a trace of biology and a quirk of chemistry is perilously thin. Some of the most intriguing candidates come from Western Australia, where layered rock formations called stromatolites have been held up as possible evidence of Earth's earliest living communities. Yet every claim raises the same skepticism. Are these really the signatures of life, or could the Earth itself, without biology, have built them? Stromatolites are layered structures formed by the trapping, binding and cementation of sediment by microbial mats, especially cyanobacteria in the modern world. They can be seen today in places like Shark Bay, also in Western Australia, where mats of microbes grow in shallow, salty waters and build domes of stone, layer upon layer. These living examples give us a template. If we find ancient rocks with similar lamination and morphology, perhaps they too record microbial activity. The temptation is clear. But ancient stromatolites, particularly those claimed to be from around 3.5 billion years ago, are not straightforward to interpret. In the Pilbara Craton of Western Australia lies the Warrawoona Group, a sequence of rocks dated to roughly 3.4 to 3.5 billion years old. Within it are structures that look strikingly like stromatolites. domed, layered build-ups of sediment that resemble microbial mats growing upward over time. In the late 20th century, these were hailed as the oldest fossil evidence of life, suggesting that microbial communities were already thriving not long after Earth stabilized enough to host oceans. The implication was profound. Life emerged early, and it left its traces in rocks we could still touch. Yet geology is full of imitators. Non-biological processes can also create layered structures. Chemical precipitation from hydrothermal fluids, for instance, can produce rhythmic banding and domed forms that look deceptively like stromatolites. The pressures and heat of billions of years of metamorphism can also alter rocks in ways that mimic biological textures. The challenge, then, is distinguishing true biosignatures from abiotic lookalikes, and that is far harder than it sounds. One line of evidence comes from the fine textures of the layers themselves. In modern stromatolites, microbial mats trap sediment grains and produce characteristic wavy laminations, sometimes with microfossil filaments preserved within. When scientists examine ancient candidates under the microscope, they look for similar microtextures, for carbon-rich films that might represent degraded organic matter, and for isotopic signatures that hint at biological activity. In the Warrawoona stromatolites, some of these features seem to be present, though never beyond dispute. Later reanalyses have cast doubt, suggesting that the supposed microbial fabrics might instead be artefacts of mineral growth. A similar debate surrounds structures from the Strelley Formation, also in Western Australia, dated to about 3.4 billion years ago. These rocks contain beautifully preserved domical and conical laminations that, to many eyes, resemble stromatolites built by microbial mats in shallow marine settings. Advocates argue that their morphology, diversity and context make a strong case for a biological origin. Skeptics counter that without direct microfossils or chemical markers, morphology alone is not proof. After all, geology has a way of fooling us. Part of the difficulty is that we are dealing with a deep past, where evidence has been overprinted by time. Heat, pressure and chemical alteration erase the subtler traces of biology. What we are left with are shadows, patterns and possibilities. To declare them life requires extraordinary caution. Yet, even if any one claim remains contested, the cumulative picture builds weight. We have multiple sites, from Australia to South Africa, where stromatolite-like structures appear in rocks of similar age. We have isotopic evidence of like carbon, carbon-12 enriched relative to carbon-13, suggesting biological fractionation around 3.5 billion years ago. We have microfossil candidates, though often degraded and ambiguous. Taken together, the case grows stronger, even if every individual piece remains debatable. The heart of the matter is epistemological. What counts as evidence for life when we have no ability to observe it directly? In paleontology, we are used to bones and shells, tangible relics of organisms. But in the Archean eon, there were no bones, no shells, no hard parts at all. Life, if present, was microbial, soft-bodied, and ephemeral. The fossils it could leave behind are not skeletons, but patterns, chemical, structural, isotopic. We are forced to interpret indirect signals, and our interpretations shift as methods and perspectives evolve. It is worth remembering that even in younger rocks, stromatolites have sometimes been misidentified. Structures once thought to be microbial have later been reassigned to purely abiotic processes. Conversely, structures once dismissed as chemical oddities have later been vindicated as biogenic, after better evidence emerged. The debate is not a flaw of science, but its very process, cautious, self-correcting, and aware of uncertainty. Today, many researchers accept that at least some of the 3.5 billion-year-old stromatolite-like structures are indeed the work of microbes. But this acceptance is often couched in humility. The case is persuasive, not definitive. What makes it persuasive is not just the morphology, but the geological context. Shallow marine settings with conditions suitable for microbial mats, coupled with the similarity to younger, less ambiguous stromatolites. The probability aligns with biology, even if absolute proof eludes us. The haunting question that lingers is this: how much evidence do we need before we are willing to declare the presence of life? If we demand the clarity of a skeleton, we will never find it in the Archean. If we accept the balance of probabilities, then stromatolites may indeed be our first fossils. Yet the risk is always there that we are seeing life where there is only chemistry. Perhaps that risk cannot be fully eliminated. Perhaps it's the price of peering so far into deep time. So, are we really looking at the oldest life, or just weird rocks? The honest answer is both. Some of the structures are likely biological, others not. Some are genuine fossils of microbial communities that lived billions of years ago. Others are tricks of minerals shaped by water and pressure. The line between them is blurred, and maybe it always will be. But even that ambiguity is a kind of truth. It tells us that the transition from geology to biology was subtle, layered, and difficult to pin down. Life did not begin with a clear signature. It began with whispers in the stone, and we, billions of years later, are still learning how to listen. How did 4 letters become the language of all life? It is a question so fundamental that we often take it for granted, as though it were inevitable that every cell on Earth would run on the same 4 bases strung together in triplets to specify amino acids. But inevitability is an illusion. The genetic code, with its elegant yet strangely arbitrary assignments, could have been otherwise. And yet, as far as we can tell, it never was. From microbes to mammals, from ancient bacteria to towering trees, all of life shares the same code. Its universality is one of the deepest mysteries in biology. Was it an accident frozen in place by chance? Or does it reflect some deeper algorithm, a rule of chemistry or logic that life could hardly avoid? To ask this question, we must first step into the world of molecules, around 3.8 to 3.5 billion years ago, when the first systems resembling life began to inherit traits from one generation to the next. This inheritance required a mapping, a way of connecting information stored in nucleic acids with the building blocks of functional molecules. The code is that mapping. It tells the cell that a sequence like AUG corresponds to methionine, or that UUU stands for phenylalanine. Each triplet or codon points to an amino acid. It is a dictionary with 64 possible words and 20 meanings, plus punctuation marks. Its logic is strange to us, not entirely regular, yet profoundly conserved. That strangeness is what makes its origin such a puzzle. One way of thinking about the code's origin is to see it as an accident of history. Perhaps in some early molecular system, certain nucleotides just happened to align with certain amino acids through crude chemical affinities or happenstance interactions. Once a working system arose, however arbitrary, it provided enough stability to propagate. Later changes would have been catastrophic, because altering the dictionary midstream scrambles the instructions for every protein. Thus, the first mapping was locked in, not because it was the best, but because it was the first. This is sometimes called the frozen accident hypothesis, a phrase that captures both the randomness and the permanence of the event. Yet the code shows patterns that suggest more than pure accident. It is arranged in such a way that errors, whether from mutations or mistakes in translation, often substitute chemically similar amino acids. A single base change might swap one hydrophobic residue for another, rather than something radically different. This minimizes the damage of errors, as though the code had been shaped by natural selection to reduce harm. If it is a frozen accident, it is a remarkably forgiving one, with built-in fault tolerance. Was that merely luck, or the outcome of selection at the molecular level? Theories abound. One proposes that the assignments reflect direct chemical affinities, that certain amino acids physically interact with their corresponding codons or anticodons. This stereochemical theory suggests that the code's logic is rooted in the chemistry of molecules themselves. Experiments have shown some weak affinities between specific triplets and certain amino acids, but not enough to explain the full system. It is as though the chemistry provided a nudge, but not the whole structure. Another theory envisions a coevolution of the code with metabolism. As early biochemical pathways expanded and new amino acids became available, the code gradually assigned triplets to them. Simpler amino acids like glycine and alanine may have been incorporated first, while more complex ones were added later as pathways evolved. This would explain why certain families of codons cluster chemically related amino acids together. The code, in this view, is a historical record of biochemistry growing in sophistication, A third perspective emphasizes error minimization. In a chaotic world where copying and translation were prone to mistakes, any mapping that reduced the harmful consequences of errors would have been favored. Through trial and error, molecular systems with more robust codes outcompeted less robust ones. Over time, this could sculpt the near-universal code we see today, one that is not perfect, but statistically optimized against damage. The universality itself raises another question. Why only one code? In principle, many different codings could work, and in fact, a few organisms and organelles today use minor variants. But across the main tree of life, the code is overwhelmingly the same. That suggests either an early bottleneck, one lineage spread and displaced all others, or that the code structure was uniquely robust and became dominant through molecular natural selection. In either case, the persistence of this shared language across billions of years is extraordinary. We must also consider how the code interfaces with the machinery that reads it. Transfer RNAs act as adapters, pairing codons with amino acids, while ribozymes or ribosomal proteins enforce the rules. For the code to exist, this whole system had to cohere, each part reinforcing the others. It is difficult to see how such complexity could arise all at once. This is why so many scientists view the code as the product of gradual refinement rather than sudden invention. Early codes may have been simpler, with fewer amino acids and less redundancy. Over time, they expanded and optimized until they reached the nearly universal form we see today. And yet, despite all these theories, we cannot say with certainty why the code looks the way it does. We know it is universal. We know it minimizes errors. We know it bears hints of chemistry and history. But whether it is ultimately an accident, an adaptation, or some deeper necessity of molecular logic remains unresolved. This humility is important. Too often we imagine that science must provide a single neat answer, but with the genetic code we face a riddle that may never be fully solved. Our evidence is indirect, drawn from the frozen traces of ancient biochemistry, and from experiments that can only approximate conditions of the deep past. We can model, we can test affinities, we can simulate evolution, but we cannot watch the code being born. Still, the haunting question lingers. Is the genetic code the way it is because it had to be, or simply because it happened to be? If it is necessity, then perhaps any life in the universe will converge on something like our four-letter system. If it is chance, then alien life may write its instructions in a completely different alphabet. Our code could be just one of countless possible dictionaries, meaningful only on this planet in this lineage. Either way, the fact remains, 4 letters, arranged in triplets, became the language of all life on Earth. Every cell is fluent in it. Every organism depends on it. Every lineage carries its imprint. Whether by accident or algorithm, it is the most successful information system in the history of the planet. And it began in the shadows of the Archean Aeon, when chemistry first began to speak. The real mystery is not only how this code arose, but why it has endured so perfectly across 3.5 billion years. What locked it in? And could we ever imagine a world where life speaks a different language? That, perhaps, is the question that will follow us long after we stop asking how the code began. Did viruses come before cells? The question has haunted biologists for more than a century, because viruses seem to straddle the boundary between life and non-life in a way that makes definitions slippery. They cannot replicate on their own, they cannot metabolize, they cannot sustain themselves without a host, and yet they are built from the same nucleic acids and proteins as all recognized life. They carry genetic information, they evolve, they leave fossils in the form of viral sequences embedded in genomes. Some scientists argue that they are nothing more than runaway fragments of cellular machinery. Others suspect that they are survivors of a much older world, one that may have preceded the first true cells. If the latter is true, then viruses might be not merely parasites, but living fossils of a pre-life chemistry that has otherwise vanished. To appreciate this debate, we must recall the stage of Earth roughly 4 billion to 3.5 billion years ago, when molecules were only beginning to assemble into more coherent systems. If an RNA world really existed, filled with self-replicating ribozymes, then fragments of RNA that could package themselves and hijack the replication of others might well have been among the first replicators. That's essentially what a virus is, a packet of genetic information that uses the machinery of something else to multiply. In a precellular world where copying enzymes and replicating strands were already in flux, parasitic elements could easily have emerged. Some might argue they were inevitable, but the problem is circular. A virus today cannot exist without a host cell. Remove the cell and the virus is inert. This suggests that viruses must have come after cells since they depend on them. Yet the counter-argument is that the very idea of a virus may not have meant the same thing billions of years ago. What we now call viruses may have originated as free-floating genetic elements in an RNA-rich environment, capable of co-opting whatever primitive enzymes or catalysts were nearby. They might have been autonomous before the invention of modern cells, only becoming dependent once cells became the dominant players. This view finds some support in the strange complexity of certain giant viruses discovered in the last 2 decades. These viruses are so large that they rival bacteria in size, and their genomes carry hundreds of genes, including some involved in protein translation. They blur the line between virus and cell. Their existence suggests that viruses might once have been more autonomous than they are today, shedding functions as they became specialists in parasitism. If so, perhaps they are remnants of once-free replicators that lost independence. Another perspective is that viruses represent escaped fragments from cells rather than ancestral forms. According to this escape hypothesis, genetic material such as plasmids or transposons acquired the ability to move between cells, wrapping themselves in protective protein coats. Over time, these escaped elements evolved into the viruses we see today. This view makes viruses latecomers in the history of life, not relics of its earlier stages. A third theory, the reduction hypothesis, suggests the opposite, that viruses were once more complex, even cellular, and gradually shed functions until only the parasitic core remained. In this case, viruses might descend from ancient cellular lineages that went extinct except in this highly reduced form. Each hypothesis captures part of the truth, but none is fully satisfying. The real difficulty lies in the definition of a life itself. If we require metabolism, independence, and self-sustaining growth, then viruses are not alive. If we require evolution, heredity, and molecular continuity, then viruses are certainly alive. They occupy a liminal space, half alive and half dead, depending on where one draws the line. That ambiguity may be a clue that the line itself is artificial. In the context of origins, viruses are fascinating because they force us to think about replicators in a broader sense. Life may not have begun as neat, independent cells, but as a swarm of competing and cooperating molecules, some with catalytic functions, some with informational roles, and some behaving parasitically. In such a world, virus-like entities would not have been an exception, but a natural part of the ecosystem. Parasitism, it seems, is not a late invention, but may have been present from the very beginning. We also see echoes of this in the genetic record. Modern cells bear traces of ancient viral infections in the form of integrated viral sequences. Entire groups of viruses appear to have ancient origins, with lineages stretching back billions of years. Although the details are murky, the persistence of viral forms suggests they are not accidents of recent evolution, but long-standing participants in the story of life. It is worth pausing to note the irony here. If viruses really are that ancient, then they may have been among the earliest examples of evolution by natural selection, shaping and being shaped by other replicators long before complex organisms arrived. In that sense, viruses might not just be parasites of life, they might have been part of life's invention, and yet we are still left with the haunting paradox. If viruses predate cells, then what were they parasitizing? If viruses arose after cells, then how do we explain their uncanny resemblance to imagined relics of an RNA world? Both possibilities stretch our understanding. Perhaps the truth lies in a hybrid picture. Some viruses are ancient fragments of precellular replicators, while others are later escapees from cellular machinery. The viral world we see today may be a mosaic, a living archive of different origins. The question we are left with is whether we can ever untangle these origins. Viruses leave little fossil record. Their sequences mutate rapidly, erasing deep history. The evidence we have is indirect, inferred from patterns and probabilities. We can build trees of relationships, trace hints of ancient genes, an experiment with how replicators might behave under prebiotic conditions. But the line between before cells and after cells may remain forever blurred. So did viruses come before cells? Perhaps some did. Perhaps what we now call viruses were once the free agents of a chaotic molecular world, only later captured and domesticated by cells into parasitism. Or perhaps all viruses are merely shadows cast by cellular life, fragments that remind us how messy evolution can be. Either way, their existence tells us something profound. Life was never a clean ascent from chemistry to cell, but a tangled web of molecules, parasites, and opportunists. And that leaves us with a haunting question. If viruses are half alive and half dead, relics of a world we can barely imagine, then what does that say about the boundary we draw between living and non-living? Was life itself, in its beginning, something half alive? Perhaps the very first sparks of biology were not tidy cells, but restless fragments, some of which survive as viruses, carrying whispers from a world before life as we know it. Who was the ancestor of everything alive today? The idea that every bacterium in the soil, every fern in a rainforest, every mushroom in a field, and every human listening to this voice could trace its lineage back to a single common ancestor, is both staggering and strangely intimate. This ancestor is not the first life, nor the one that invented replication, nor the lone spark from chemistry into biology. Instead, it is the one that stands at the root of the tree of life as we know it, the organism whose descendants never died out and diversified into all branches of bacteria, archaea, and eventually eukaryotes. Scientists call it LUCA, the last universal common ancestor. LUCA is not a mythic Adam or Eve. It was not alone, nor was it the first living thing. Rather, it was part of a population of organisms, and from that population, one lineage persisted and branched while others vanished. When we speak of LUCA, we speak of the organism whose features we can infer by comparing what all modern life still shares in common. In this way, LUCA is less a fossil in stone and more a fossil in code. Its traces live in our genetic toolkit, in the universal molecules and reactions without which life does not function. The timeline of LUCA is thought to fall somewhere between 3.5 billion and 3 billion years ago. By this time, Earth already hosted microbial ecosystems, as suggested by stromatolite-like structures and isotopic signatures of carbon. But within that microbial world, one lineage carried the hallmarks that unite us all. To reconstruct LUCA, scientists look not at rocks but at genomes. The logic is simple. If every living organism today shares a particular gene or process, then LUCA likely had it too. If some lineages lack a feature, it may have evolved later. Through this comparative method, researchers can strip away differences and approach the shared core. So what do we think LUCA had? The clearest clues come from the genetic code itself. All life uses the same 4-letter nucleic acid alphabet and the same triplet-based codons to specify amino acids. This strongly implies that LUCA had DNA or RNA storing information and a translation system to convert that information into proteins. The universality of ribosomes, those molecular machines that stitch amino acids together, suggests that LUCA had ribosomes of its own. These were probably smaller and simpler than modern ones, but recognizable in their essential function. In fact, ribosomal RNA is one of the strongest molecular fossils we possess, its core structure conserved across all domains of life. LUCA also seems to have had a fairly rich metabolic toolkit. Analyses of thousands of modern genomes have allowed scientists to reconstruct a set of around 300 to 400 core genes that may trace back to LUCA. Among them are enzymes involved in nucleotide synthesis, amino acid pathways, and lipid metabolism. The presence of these suggests that LUCA was not a simple replicating strand but a cell-like organism with organized biochemical pathways. Perhaps most intriguing is what LUCA's metabolism hints about its environment. Many of the genes inferred for LUCA are linked to enzymes that handle hydrogen, carbon dioxide, and simple compounds like formate. This points toward a lifestyle dependent on chemolithoautotrophy, deriving energy from inorganic chemical reactions, not sunlight. Some researchers argue this places LUCA in an environment rich in hydrogen and carbon dioxide, such as the alkaline hydrothermal vents on the ocean floor. In such settings, Proton gradients and mineral surfaces could have fueled the redox reactions on which LUCA thrived. Yet LUCA was not photosynthetic. Genes associated with harvesting light are absent from the reconstructed core. Likewise, LUCA does not appear to have possessed the full modern complement of DNA replication enzymes, suggesting that its genetic system was simpler than that of its descendants. In this way, LUCA was advanced compared to prebiotic replicators, but still primitive compared to modern microbes. One of the challenges in talking about LUCA is that we risk imagining it as a single individual. In truth, LUCA was likely a population of organisms with genetic diversity. Some lineages within that population gave rise to bacteria, others to archaea, and eventually, through symbiosis, to the lineage that became eukaryotes. The point is not that one special microbe sat alone in a tide pool, but that a community of related organisms occupied some niche, and from them sprang all subsequent life. What LUCA was not is equally important. LUCA was not the first life on Earth. By the time it existed, life had already diversified, and many forms left no descendants. LUCA was not a single common ancestor of all possible replicators, but simply the ancestor of everything still alive today. Other branches, once real and vital, are gone. LUCA is the survivor, not necessarily the innovator. Even with these reconstructions, the picture remains frustratingly incomplete. We can infer what LUCA had by comparing genomes, but genes can be lost as well as gained. If some early lineage discarded a feature, we might misinterpret its absence as meaning LUCA never had it. Horizontal gene transfer, the swapping of genes between microbes, further muddies the water. Genes can spread across lineages, making it difficult to tell whether LUCA invented them or whether they spread later. The LUCA we imagine may therefore be both more and less than the historical truth. Still, the consensus is that LUCA was a thermophilic, anaerobic organism living in an environment rich in hydrogen, metals and carbon dioxide. It probably had a rudimentary version of the genetic code, a translation system, ribosomes, and a suite of enzymes for building the basic molecules of life. It could make proteins, nucleotides, and lipids. It could exploit redox reactions for energy. It was already sophisticated enough to look familiar to us, but it would not have resembled any modern cell in detail. The search for LUCA also raises a philosophical question. When we say universal ancestor, we imagine a neat tree branching backward to a single root. But evolution is messy. Early life may have been more like a web than a tree, with frequent gene exchange blurring distinctions. LUCA, then, may not have been a solitary root, but rather the average of a network of gene-sharing organisms. In this view, LUCA is not an individual but a statistical construct, the point where the histories of genes converge, even if the histories of organisms were more tangled. The legacy of LUCA is undeniable. Every breath of oxygen you take, every protein that folds in your cells, every codon read by a ribosome, carries a continuity that stretches back over 3 billion years to that ancestral population. It is humbling to realize that the unity of life is not a poetic metaphor but a literal genetic fact. And yet the haunting question remains. We can reconstruct LUCA's toolkit and speculate about its home, but we may never meet it directly. Fossils of microbes that old are ambiguous, and molecular clocks can only reach so far. LUCA is forever behind a veil, known only through the echoes it left in our chemistry. So we are left to wonder, if LUCA is our universal ancestor, how many other ancestors were there that left no trace? How many lineages thrived in those early eons, only to vanish completely? And if LUCA was just one survivor among many, what accidents of history preserved its line over all others? In asking who LUCA was, perhaps the deeper mystery is who we might have been, had another lineage endured instead. What if life had taken another path entirely? We take it for granted that carbon, water, and the double helix of nucleic acids were the inevitable outcome of chemistry on Earth, but there is no guarantee written into the laws of the universe that it had to be so. When we look back to those early billions of years, we can ask not only how life did begin, but how it could have been different. Could there have been alternative chemistries, parallel biospheres, or even a shadow life that slipped away before we ever appeared to notice? The first question always circles back to carbon. Carbon is the element at the centre of our biology, the backbone of sugars, lipids, proteins, and nucleic acids. Its appeal lies in its extraordinary versatility. Carbon atoms can bond with up to 4 other atoms, allowing them to form long chains, rings and branching structures. This flexibility makes it possible to build both sturdy molecules and highly reactive ones, a balance that life exploits for structure and function alike. But chemists have long wondered, is carbon truly unique in this, or could another element have played the same role? Silicon is the most obvious candidate, sitting just beneath carbon on the periodic table and sharing some of its bonding properties. In science fiction, silicon-based life has often been imagined as crystalline, rocky or mineral-like. In theory, silicon can also form 4 bonds, just like carbon, suggesting it might support complex molecules. But there are practical challenges. Unlike carbon, silicon struggles to form stable long chains in watery environments. Its preferred bonds are with oxygen, and when silicon binds oxygen, the result is often rigid and crystalline rather than flexible and dynamic. Silicon dioxide, better known as quartz, is a common mineral but not a medium for biochemical complexity. Yet it would be a mistake to dismiss silicon entirely. Under different environmental conditions, silicon chemistry might flourish. For example, in environments with little water and abundant methane or ammonia, silicon might bond in more varied ways. Laboratory experiments have even shown that, under controlled conditions, chemists can coax silicon into forming more carbon-like structures. One study demonstrated that certain enzymes can forge bonds between silicon and carbon, hinting that biology itself could open doors that chemistry alone does not. Still, on Earth, with its watery oceans and oxygen-rich crust, carbon had overwhelming advantages, leaving silicon to become the skeleton of rocks rather than the skeleton of cells. Another speculation is whether life could have used an entirely different solvent. On Earth, water is the universal medium. Its polarity allows it to dissolve a vast range of substances, and its high heat capacity stabilizes environments. The hydrogen bonds between water molecules create both flexibility and cohesion, letting molecules interact dynamically without collapsing into chaos. But what if Earth had lacked oceans of liquid water? Could other solvents have played the role of life's cradle? Ammonia, for instance, is often suggested as a water alternative. It is liquid at lower temperatures, and its molecular properties allow for hydrogen bonding, though weaker than water's. Ammonia-based life might thrive in colder environments, where water would freeze solid. Hydrocarbons like methane or ethane provide another possibility. On Saturn's moon, Titan, lakes of liquid methane and ethane glisten under a thick orange atmosphere. Some scientists wonder if exotic life could arise there, substituting hydrocarbons for water as the medium of exchange. Such life would run at a slower pace, with reactions proceeding sluggishly in the cold, but perhaps patience is another form of adaptation. Even on Earth, one might ask whether alternative solvents existed in the early days. Could formamide, a liquid that can support nucleic acid chemistry, have acted as an early medium for prebiotic reactions? Some experiments have shown formamide to be a surprisingly fertile environment for forming the building blocks of RNA. Though water dominates Earth today, perhaps pockets of other solvents once nurtured chemistry before fading from the scene. Beyond solvents and backbones, we can imagine life with different information systems. Earth life encodes heredity and nucleic acids built from 4 bases, but there is nothing inevitable about 4. Synthetic biologists have engineered expanded genetic codes with 6 or even 8 bases, and demonstrated that such molecules can replicate and store information. Could early life have experimented with multiple codes before settling on the one we know? If so, those experiments left no survivors, but the possibility suggests that the path to our genetic alphabet was one among many. This brings us to the idea of a shadow biosphere. Some scientists have proposed that even today, Earth might harbour alternative life forms that do not share our biochemistry. These hypothetical organisms would use different building blocks, making them invisible to the methods we use to detect ordinary life. If they exist, they might be hiding in extreme environments, surviving unnoticed because we never thought to look with the right tools. The fact that we have not yet found them does not prove they do not exist, only that our search has been limited to the life we already know. The idea is unsettling because it suggests we may be sharing Earth not just with familiar bacteria and plants and animals, but with something entirely other, a lineage of life that branched away long before our own ancestors crystallized into being. Why then did Earth settle on the chemistry it did? Perhaps it was not inevitability but contingency. Carbon worked in water, under the conditions Earth provided, with the energy flows available. Given different temperatures, different atmospheres, or different geologies, another chemistry might have taken root. This means that if we look outward to other planets and moons, we should expect surprise. Life elsewhere may not look like life here, and it may not even register to our instruments if we're too narrow in our expectations. Yet there are reasons to think Earth's path may be more than mere chance. Carbon's bonding flexibility, water's solvent power, and the universality of chemical principles may make this combination not just convenient but deeply favourable. Perhaps any planet with liquid water and carbon will tend towards something resembling our biology. In this view, Earth's choices are not unique but common solutions to common problems. On the other hand, the stubborn difficulty of forming long chains with silicon or sustaining rapid reactions in methane suggests that life's potential chemistries are constrained, and our path may be one of the only viable ones. The haunting question is whether there was a moment, in those early billions of years, when more than one kind of life flickered into being. Could multiple chemistries have coexisted, with one eventually outcompeting the others? If so, the world we know may be the legacy not of inevitability but of survival, the outcome of a competition we will never witness. Perhaps there were once alternative living systems on Earth, silicon skeletons or ammonia-based metabolisms, washed away or consumed by the dominance of carbon in water. If that is true, then our biosphere is not simply a story of emergence but also a story of extinction, of lost possibilities erased before they had a chance to flourish. In the end, we are left with a paradox. We know only one example of life, and it is ours. That makes it both a guide and a blindfold. From within its chemistry, we try to imagine others, stretching the possibilities of carbon, silicon, solvents, and codes. We build experiments, simulate reactions, and explore moons and planets in search of something different. Yet every step reinforces how much we do not know. Were we lucky or ordinary? Was carbon inevitable or just victorious? Until we find another form of life, somewhere else, or perhaps hidden here on Earth itself, we can only speculate. And so the question lingers in the background, both humbling and thrilling. If the universe had rolled the dice again, what kind of life would have answered back? Imagine a world where the very thing you exhale with every breath was once a deadly poison. For billions of years, the early Earth was a planet of gases we would now consider suffocating. Nitrogen, carbon dioxide, methane, hydrogen sulfide, and among them, oxygen was scarce to the point of absence. It was not just irrelevant, it was dangerous, corrosive, a reactive substance that tore apart delicate chemical bonds. Life as it first arose found stability in a world without oxygen, in an atmosphere that was reducing rather than oxidizing. And then, astonishingly, some microbes stumbled upon a way of capturing energy that produced oxygen as a byproduct. They did not just invent a new pathway of life. They triggered what we now call the Great Oxidation Event, a planetary upheaval that reshaped the chemistry of the oceans, the rocks, the sky itself, and the trajectory of every lineage to come. The story begins with cyanobacteria, though at the time there was nothing inevitable about their role. These microbes were among the first organisms capable of what we call oxygenic photosynthesis, harnessing light to split water molecules, taking the electrons for energy, and releasing oxygen as waste. Water is an abundant resource, and compared to other electron donors such as hydrogen or sulfide, it offered an almost limitless supply. By learning how to tap into it, cyanobacteria unlocked an energy source vast beyond anything that had come before. But in doing so, they released a chemical that threatened the very stability of the biosphere that had nurtured them. At first, oxygen released by these microbes did not accumulate in the air. The early oceans and crust were packed with chemical sinks ready to absorb it. Iron dissolved in seawater eagerly reacted with oxygen, precipitating out as iron oxides and settling onto the seafloor. These deposits, layered band by band in ancient rock, survive today as banded iron formations, silent geological records of oxygen reacting with the seas. As long as there was unoxidized iron available, oxygen released by cyanobacteria was mopped up, bound into minerals, and hidden from the atmosphere. It is one of the ways we can trace this invisible drama across deep time. But sinks are finite. Over tens of millions of years, oxygen-producing microbes outpaced the available chemical sponges. As iron became depleted, oxygen began to linger longer in the oceans and eventually seep into the atmosphere. Around 2.5 to 3 billion years ago, this tipping point was reached. Oxygen levels in the air surged by several orders of magnitude, still low by modern standards, but enough to cause a profound shift. This is the event we call the Great Oxidation. The term itself might sound grand, but the consequences were nothing less than catastrophic for much of life at the time. To organisms adapted to an anoxic world, oxygen was toxic. It destabilized enzymes, damaged membranes, and generated reactive oxygen species that could shred biological molecules. Many lineages that had thrived in the reducing environment of early Earth likely vanished, pushed into extinction by a gas they could not tolerate. The rise of oxygen was not just an innovation, it was a mass poisoning on a planetary scale. The survivors were those that adapted, evolving new biochemical pathways to detoxify oxygen, or even repurpose it as a more efficient tool for metabolism. This is one of the great paradoxes of life's history. A waste product turned out to be both a hazard and eventually an opportunity. With oxygen available, new forms of respiration became possible. Aerobic respiration, in which oxygen serves as the final electron acceptor in energy metabolism, yields far more energy than the anaerobic pathways of earlier cells. This potential would not be realized immediately, but the groundwork was laid. Oxygen, once a curse, would become the key to complexity. Geologists trace the timing of this transformation not only through banded iron formations, but also through isotopic signals. The sulfur isotopes preserved in ancient rocks carry evidence of atmospheric conditions. Before the Great Oxidation, strange mass-independent fractionations of sulfur isotopes occur, signatures that could only exist in an atmosphere without much oxygen. Afterward, those signals disappear, replaced by ones consistent with an oxidizing sky. This line of evidence suggests a dramatic and irreversible shift in atmospheric chemistry, one that altered weathering, climate, and the cycling of elements across the planet. The Great Oxidation event also had global environmental consequences. Methane, a potent greenhouse gas, was likely abundant in the pre-oxygen atmosphere, produced by methanogenic microbes. Oxygen reacts readily with methane, breaking it down into carbon dioxide and water. Carbon dioxide is a weaker greenhouse gas than methane, and so as oxygen rose, Earth may have cooled dramatically. Some researchers argue that this cooling triggered what are known as the Snowball Earth episodes, global glaciations where ice extended close to the equator. If true, then the Great Oxidation was not only a biochemical revolution, but a climatic upheaval, plunging the planet into deep freezes that would challenge the survival of all organisms. What is remarkable is not just that life invented oxygenic photosynthesis, but that it endured the consequences. Cyanobacteria themselves must have faced the same threat from their own waste product. Yet they survived, evolving protective mechanisms to neutralize reactive oxygen species. Enzymes like superoxide, dismutase, and catalase may have their origins in this period, functioning as shields against oxygen's destructive chemistry. For other microbes, survival likely meant retreating to niches still sheltered from oxygen, such as deep sediments, hydrothermal systems, or isolated anoxic environments. Even today, many anaerobes persist, remnants of an older world that once dominated the planet but now occupies its hidden margins. The rise of oxygen also reshaped the geology of the planet. Minerals that could not form in a reducing world became stable, creating new types of rocks and soils. Sulfates, nitrates, and other oxidized compounds entered circulation, altering the chemistry of oceans and sediments. The cycling of carbon itself changed, with oxygen influencing both the burial of organic matter and its decomposition. In short, oxygen wove itself into the fabric of Earth's geochemical systems, inextricably linking biology with the mineral and atmospheric environment. And yet, despite all the evidence we have, much about this period remains uncertain. How gradual was the build-up of oxygen? Was it punctuated by false starts, with temporary rises followed by collapses? Some studies suggest whiffs of oxygen in the atmosphere before the main event, small-scale experiments by cyanobacteria that did not yet change the world. Why the final surge succeeded where earlier ones may have failed is still debated. Perhaps it was the exhaustion of chemical sinks, perhaps tectonic activity exposing new surfaces to weathering, perhaps ecological tipping points in microbial communities. We cannot be certain. What is clear is that the Great Oxidation event set the stage for everything to come. Without oxygen, the later rise of more energy-hungry metabolisms and eventually larger, more complex organisms would have been impossible. But in that moment, 3 billion years ago, it was not an invitation to complexity. It was a crisis, one that nearly destroyed the biosphere that had unknowingly summoned it. So we are left with a sobering reflection. Life itself changed the planet, not through intention, but as a byproduct of its hunger for energy. In chasing the sun and splitting water, cyanobacteria rewrote the rules of chemistry for every other organism. The Great Oxidation event reminds us that evolution is not always gentle or harmonious. Sometimes it is reckless, even self-destructive, and yet from that gamble new possibilities arise. The haunting question is whether life on any other world might make the same mistake. Whether it is universal for biology to stumble upon a waste product that poisons its own cradle, or whether Earth's path was a unique accident. Either way, the breath you just took carries the legacy of that gamble, the ancient poison that life learned to turn into its greatest strength. If the universe was somehow rewound and set in motion again from the very beginning, would life arise once more, or was it the product of a series of improbable accidents that will never be repeated? This is the question that haunts biologists, philosophers and astronomers alike, because it cuts to the heart of whether we are an inevitable expression of nature's laws, or simply an unlikely outcome that could easily have been otherwise. On the one hand, life feels like it fits naturally into chemistry, as if molecules lean toward complexity the way rivers lean toward the sea. On the other, the specific chain of events that led from a lifeless Earth to a biosphere rich with organisms might be so fragile and so contingent that any small deviation would have prevented it. The tension between determinism and chance runs through the history of science, and here, in the question of life's inevitability, it finds its sharpest edge. The French biologist Jacques Monod once declared that life was the product of chance and necessity, but he emphasized chance above all. In his famous line, "Man at last knows he is alone in the universe's unfeeling immensity, out of which he emerged only by chance." For Monod, the molecules that assembled into the first living systems did so by accident, without purpose or destiny, and their survival was the consequence of natural selection acting on these accidents. Change the roll of the dice, and perhaps Earth would have remained barren. In this view, the fact that we exist is extraordinary, not because it was destined, but because against all odds the random fluctuations of chemistry happened to cross the narrow threshold into life. The American paleontologist Stephen Jay Gould echoed a similar theme in his idea of replaying life's tape. If we could rewind the history of life on Earth and let it play again, Gould argued, the outcome would be entirely different. Dinosaurs might never have evolved, mammals might have remained small and obscure, and humans almost certainly would not have appeared. Contingency rules in this view. Every branch point in the evolutionary tree is a fork chosen by circumstance, an asteroid impact, a volcanic eruption, a climatic shift. Events that did not have to happen, but did, and that reshaped the possibilities available afterward. Life, in this telling, is not inevitable but precarious, a long improvisation that could just as easily have ended in silence. But there is another perspective, articulated by thinkers such as Nick Lane and Simon Conway Morris, who suggest that certain features of life are not mere accidents but convergences. Conway Morris, for example, has argued that evolutionary pathways often lead to similar solutions even when starting from different points. Eyes, wings, and echolocation evolved independently in multiple lineages. This, he suggests, shows that life is channeled by the constraints of physics and chemistry toward a limited set of viable forms. Nick Lane, focusing on metabolism, argues that the use of proton gradients, redox chemistry, and energy flows rooted in the laws of thermodynamics were not optional. They were dictated by the environment and by the universal needs of complex systems. If those constraints are so binding, then perhaps life is not an accident at all, but an expected product of any Earth-like planet with similar conditions. One way to think about it is to consider the building blocks of life as they appear in the universe. Amino acids, nucleobases, and simple sugars have been detected in meteorites, in interstellar dust clouds, and in laboratory simulations of early Earth. Their presence suggests that organic chemistry is not rare but widespread, a natural outcome of carbon's versatility. If the raw ingredients are everywhere, perhaps the leap to life is not as improbable as it seems. On the other hand, the mere presence of amino acids does not guarantee living systems. The step from molecules to metabolism, from chemistry to evolution, remains dauntingly complex. Even if the ingredients are common, the recipe might be almost impossible to follow. The debate circles around the same dilemma: inevitability versus accident. Consider water, for instance. Liquid water seems essential for life as we know it. Planets where water remains stable at the surface may therefore be promising candidates. Yet having water is not enough. Venus once may have had oceans, but runaway greenhouse effect boiled them away. Mars shows evidence of ancient rivers, but its atmosphere thinned and the surface froze. Earth's long stability may have depended on a precise balance of geological and atmospheric feedbacks. The placement of the moon, the cycling of carbon through plate tectonics, the shielding of the magnetic field, all of these may have been necessary. Were these accidents stacked improbably in our favour, or are they the kinds of conditions that will statistically recur across many worlds? The haunting part of this question is that we cannot test it directly. We cannot rewind the universe. What we can do is look outward. The search for exoplanets has revealed thousands of worlds, many of them in the so-called habitable zones of their stars. If life is inevitable, we should expect that some fraction of those worlds hosts biology, and if our instruments become sensitive enough, we might one day detect atmospheric signatures of life. If, however, the universe is filled with silence, if planet after planet appears barren despite being superficially Earth-like, then perhaps Monod and Gould were right. Life was a one-off accident, a miracle of contingency. Even within Earth's own story, the question of inevitability haunts us. Was the Great Oxidation event bound to happen once oxygenic photosynthesis evolved? Or could it have failed if tectonics or climate had shifted differently? Were multicellular organisms destined to evolve? Or was it the product of peculiar ecological pressures that might have easily gone another way? Did the emergence of intelligence depend on countless accidents, asteroid impacts, chance extinctions, climatic swings? Or was some form of sentient life an inevitable outcome of selection acting over long enough time? Each of these questions refracts the same core issue. Is evolution constrained or open-ended? The deeper we look into biology, the harder it becomes to separate necessity from chance. The genetic code, for instance, appears universal. Was this because one code was simply better, minimizing errors, and therefore inevitable? Or was it just that one lineage happened to spread and eliminate others? Convergence argues for inevitability, contingency for accident. In reality, the truth may be entangled. Some aspects of life are dictated by physics and chemistry, while others are accidents frozen into history. As a humble human reflecting on this, I have to admit we simply do not know. The arguments are compelling in both directions. If life is inevitable, then the universe may be teeming with it, though intelligence may still be rare. If it is an accident, then we may be utterly alone, a singular event in cosmic history. Both possibilities are profound and both are humbling. One tells us we are ordinary, one among countless experiments. The other tells us we are extraordinary, a fragile exception. Which is more comforting depends on how one looks at it, and so we end where we began, with the haunting question itself. If the universe were rewound, would life happen again? We may never know. The only experiment available to us is this one planet, this one history, this one fragile biosphere. We are the observers trapped within the result, incapable of stepping outside to compare it to alternatives. Perhaps that is why the question lingers with such weight. It is unanswerable, and yet in that unanswerable space lies the deepest mystery of existence. The silence of the stars, whether filled with life or devoid of it, is the backdrop to our reflection. What we do know is that life has happened here, once, improbably or inevitably. The fact itself is astonishing enough. The haunting question is whether the cosmos holds more such astonishments, waiting in the dark, or whether ours is the only voice it will ever hear. How many beginnings were lost before the beginning we know? When we talk about the history of life, we almost always start with what survived, with the lineages that endured long enough to leave a record or to become part of us. But what about the failures? The countless fragile experiments that sparked and flickered and then vanished forever. It is possible that Earth's first billion years were not a single triumphant march toward the life we know, but a graveyard of attempts, each erased before it could take hold. The very notion of extinction usually applies to organisms and species, but here we have to stretch it back into prehistory, to imagine extinction at the level of proto-life, of fragile chemistries that almost became alive but did not. When Earth cooled after its fiery youth, around 4 billion years ago, its surface was not empty but restless. Oceans churned with energy, volcanic gases vented into the air, minerals interacted with organics, and cycles of wetting and drying or heating and cooling pushed molecules into combinations. We know from laboratory experiments that amino acids can form, that lipids can assemble into tiny spheres, that energy gradients can drive reactions toward complexity. But complexity is not the same as persistence. For a proto-life to survive, it had to find stability in a chaotic world. A bubble of lipids enclosing some molecules might have been a step toward a cell, but unless that bubble could divide, grow, or draw energy from its surroundings, it would collapse or dilute into nothing. Multiply that by millions of trials across millions of years, and you begin to sense how many beginnings likely never went anywhere. This idea is sometimes called a shadow biosphere, not in the sense of life existing secretly alongside ours today, but in the sense that there may have been whole lineages of proto-organisms that thrived for a geological blink and then disappeared. Imagine a chemistry that built itself not on nucleic acids, but on some other repeating molecule, perhaps peptides strung together by chance reactions. Perhaps such systems even managed some crude self-replication, enough to linger in pools or along vent walls. Yet if they lacked the robustness to withstand fluctuations, or if they could not compete with other chemistries that captured energy more efficiently, they would have vanished without trace. Rocks do not keep records of molecules that never fossilized. The evidence of these experiments would have dissolved, leaving behind only the ghost of possibility. It is humbling to think that the history of a life we know might be only the survivor's tale. Everything we study, the genetic code, the metabolic pathways, the universality of certain molecules, comes from the line that did not vanish. But why this line, and not another? Perhaps it was simply better adapted. Perhaps it stumbled on a chemistry that was more stable, or more efficient at harvesting energy. Or perhaps, by luck, it was in the right place at the right time, protected from cataclysms that wiped out rivals. We cannot know, because history remembers only the victors. Yet logic suggests that if one chemistry succeeded, many others must have failed first. Extinction at this level would have been absolute. When a species disappears today, it leaves fossils or genes in related organisms or ecological effects. But when a proto-life fails, it leaves nothing. Its molecules revert to the background soup, indistinguishable from any other organic residue. That makes this kind of extinction particularly haunting, because it erases not only the lineage but the memory of its existence. We are left to infer its presence only from the improbability that life could have arisen in a single, unbroken stroke. Think about it in evolutionary terms. Modern evolution is incremental. Mutations accumulate and selection refines them. The path is gradual, step by step. But the origin of life was not gradual in the same way. It required crossing thresholds, from non-living chemistry to self-replicating systems, from fragile molecules to compartments, from random cycles to sustained metabolism. Each threshold would have had many failed crossings. Molecules might have replicated, but too inaccurately. Compartments might have formed, but failed to persist. Metabolisms might have sparked, but lacked balance. Each of these would have been a beginning, and each could have been an end. Some scientists imagine that whole rival protobiospheres may have existed. Not just scattered molecules, but networks of reactions and structures that functioned as primitive living systems, alien to us, but alive by any reasonable standard. For a time, they may have even dominated certain environments, thriving in volcanic pools or colonizing shallow seas. but if their chemistry was incompatible with the emerging systems that would lead to our ancestry, they may have been outcompeted and erased. In that sense, extinction at life's dawn may have been brutal competition among rival chemistries. Only one set of solutions survived to spread everywhere, drowning out all others until they were gone. The timescale of these ghost beginnings is itself sobering. Between 4 billion and 3.5 billion years ago, Earth endured heavy bombardment from space, tectonic upheavals and chemical instability. Any fragile proto-life could have been wiped out repeatedly by impact sterilizations or shifts in ocean chemistry. Survival required not only robust chemistry, but also resilience against planetary violence. That resilience may have been rare. Perhaps dozens of beginnings were erased before one could persist long enough to root itself into geology and begin the slow trajectory toward biology as we know it. It is tempting to picture these failures as tragic, but that may be the wrong lens. They were not organisms with experiences or struggles. They were chemical systems running or failing depending on their stability. Yet in another sense, their disappearance is profound, because it reminds us that life as we know it is not the only way life could have been. We live in the world shaped by the survivors, but the diversity of what might have been is unknowable. There may have been proto-lives that used different solvents, or different elemental backbones, or entirely different logics of heredity. Their extinction means we will never know those possibilities. This silence in the record is an uncomfortable gap in science. We want to trace a neat progression from chemistry to biology, but the evidence is filtered by survival. We can model, simulate and theorize, but the actual history is hidden. Perhaps it is buried too deep for us ever to uncover. Perhaps it is simply gone. When we look at ancient rocks and search for microfossils or isotopic signatures, we may be seeing only the last stage of a much longer sequence of failed beginnings. The true dawn of life could have been far messier than we imagine. What does this mean for the universe beyond Earth? If life here required many failed experiments before one succeeded, then the odds of success elsewhere might be lower than optimists hope. It might mean that most planets with rich chemistry never cross the thresholds, or that they flicker with short-lived proto-lives that never stabilize. On the other hand, it could mean that failure is part of the process, and that given enough time and trials, life will always emerge somewhere. Once again, we find ourselves at the crossroads of accident and inevitability. As a human speaking humbly, I have to admit that this line of thinking is speculative. We cannot prove that multiple proto-lives existed, nor can we identify their traces. But the logic of extinction, the sheer improbability of hitting the right combination on the first try, suggests strongly that they did. The absence of evidence is not evidence of absence, but the possibility lingers. We live in the aftermath not only of one success, but of countless erasures. And that brings us back to the haunting question. How many beginnings were lost before the beginning we know? We may never find their fossils, their chemical imprints, or their stories. They are gone more completely than any extinct species could ever be. All we have is the inference that our path was not the only one tried. In the silence of the rocks, in the gaps of the record, there may be the faintest echo of those ghosts. Extinct beginnings that almost were, but are no more. If life is rare in the universe, it may be because most beginnings never make it past those fragile first steps. And if life is common, it may be because extinction and persistence are simply two sides of the same cosmic experiment. The ghosts remind us that our existence rests on the edge of what was possible, and that the story of life is not only about survival, but about everything that did not survive. What does it mean that everything alive today, from the smallest bacterium to the tallest tree to us sitting here, shares one ancient moment of origin? It is one of the strangest truths in all of science, that no matter how much diversity exists, no matter how far branches of life have spread, there is a point behind us where the branches meet, where time narrows into a single living thread. That is the first handshake with time, the moment when the ongoing continuity of life truly began. It was not the birth of Earth itself, nor the first molecule to form in a pool or a vent, but the point at which something crossed the threshold from chemistry into biology, and held on long enough never to let go again. Every second since then, every day, every age carries that unbroken chain. Revealing this is unsettling because it forces us to confront how fragile and yet how stubborn life is. If that moment had never happened, there would be no memory, no language, no questions like this. Earth would still spin, tides would still fall and rise, volcanoes would still breathe gases into the air, but there would be no eyes to see, no minds to reflect, no continuity. And yet it did happen, in a way that endures so completely that even now, billions of years later, the cells in your body are still repeating the same patterns, the same chemical dialogues, the same genetic logic that began then. What we are, biologically speaking, is an echo of that event replaying across 4 billion years. The information contained in every genome is not just a list of instructions for one organism, but a fossil of decisions made long ago. The very fact that life uses 4 bases for its code, that it transcribes and translates with the same fundamental machinery, that it draws energy from gradients and preserves its boundaries with membranes. These are not arbitrary. They are signatures of choices locked in at the dawn, not by intention but by accident and survival. It means the living world is not infinite in its possibilities. It carries the inertia of that first origin, narrowed into the path we all walk today. It also means that time, which we normally think of as devouring everything, has here done the opposite. Time has preserved. Every breath of oxygen you take, every heartbeat, is powered by molecular systems that trace back through a continuity so deep it is hard to fathom. The molecules themselves are recycled. Atoms pass through you from ancient stars and rocks, but the pattern, the rhythm of replication, metabolism, inheritance, has never stopped. Time has not broken it once. That is the single most astonishing fact we know, not just that life arose, but that it has never gone away. We often think of extinction as the end of lineages, and rightly so, but the truth is that extinction has been everywhere since the beginning. Whole species vanish, entire families disappear, and even early forms of proto-life likely flickered out before real life took hold. And yet, through all that loss, one thread continued. We are not separate from it. We are it. There is no living thing on Earth that does not carry the continuation of that same initial chemistry. That is why biologists sometimes say all life is one family. It is not a metaphor. It is literal. The differences we see today are real, but they are built on a shared root that has never been severed. What remains is the haunting question of meaning. What does it mean that we are all part of one origin? One interpretation is humility. We are not special in our aliveness. We are extensions of something ancient and shared. Another is connection. The fact that a tree, a fungus and a whale share the same underlying toolkit means kinship is more than poetry. It is molecular fact. And another is chance. Perhaps this continuity is only here because of a fragile accident, a lucky sequence of conditions that might never be repeated anywhere else. Scientists debate whether life was inevitable or improbable, whether chemistry was destined to produce something that could persist, or whether it was a once-in-a-universe fluke. What we do know is that once it began, continuity became the law. There has been no second genesis on Earth that we can detect, no rival life that developed independently and still thrives alongside us. All known life belongs to the one origin. The silence of alternatives only emphasizes the weight of that first success. If you stand outside at night and look at the stars, you're seeing the context. Those other suns may host planets with oceans and atmospheres with rich chemistry. Some of them may have their own origins, their own handshakes with time. But from here, all we know is this one. The connection is so intimate that your cells today are, in a sense, the living continuation of that earliest event. Not descendants in the abstract, but the actual process itself, carried forward in unbroken sequence. The proteins folding in your body tonight, the ATP cycles spinning in your cells, are not different in principle from those that ran in the first cells. Life is not a metaphor for continuity. Life is continuity. We sometimes look for fossils to tell us when life began, but the truest fossil is inside every cell. The chemical language and machinery we all use is a living imprint of the origin itself. Rocks may be ambiguous, debates may rage about stromatolites or isotopes, but your genome is not ambiguous. It is the legacy of the first. That should be a reminder that we are not merely studying something outside ourselves. We are studying our own deep past, written into what we are. The resolution of this reflection may not be comforting. If life began once, it could have failed. If it failed, there would have been nothing to carry forward. That is the razor-thin chance on which all history rests. Yet it did not fail. It persisted. It adapted. It endured cataclysms, bombardments, and poisonings, and it still breathes in us. The first handshake with time was fragile, but once made, it held on with unimaginable persistence. And so we end with a haunting question, the same one that echoes across all of science and philosophy. Why did it happen at all? Why was there one thread and not none? Why are we here, still carrying the rhythm of an event almost 4 billion years old? We may never answer it fully, but every time you exhale, every time a cell divides, every time a bacterium reproduces in the deep ocean, the answer is being enacted in silence. The handshake was made and it has never been broken. The meaning is not written outside us, it is us. Thank you, fellow sapiens, for wandering this timeline with me, for drifting into deep time, for slowing down and remembering. If this helped you fall asleep, helped you study, or simply helped you step out of the noise for a while, thank you for being here. If you think more people should know this story, you know what to do. Like, subscribe, share it with the sapiens in your life, and tell me, are you listening before bed, while working, or somewhere in the world I can only imagine? And as always, stay curious, stay calm. I'll see you in the next story.